So good morning, everybody. We are still waiting a few minutes for the people to join. And I would like to remind you that we are uploading some of the pictures from yesterday on the website of the conference, but also on a dedicated album on Flickr that you will find the link on the conference website. And then, of course, as we did yesterday, we will cover the sessions through the LinkedIn page of Seamless PV. So in 5 minutes we start, so enjoy the second day of the conference.
So good morning, everyone, and welcome to the second day of the IPV conference here in Florence. We start today with the first session dealing with BIPV, operational experience and reliability. We heard quite a lot yesterday about BIPV technology. Today we are moving a bit from the PV modules up to the testing of the PV module and toward the system dimension. So how to better characterize and provide good reliability and good information regarding BIPV modules and system. I'm not Philippe Massé, that unfortunately was not able to join us due to some strikes in Belgium, and I will take over the co-chairing of this session together with Sergio Matalucci from PV Magazine. So we have roughly 70 minutes in this session, so I'll ask really the speaker to try to be on time. A bit less than 10 minutes would be great so that we have time at least for one question. So without taking too much time, I would like to invite to the podium Joseba Ormachea from Tecnalia in Spain. He will make a presentation on development and application of new extended stress sequences to characterize durability of BIPV module. Joseba, the floor is yours.
All right. Thank you very much for your kind introduction, Francesco. All right, I have the control of the slides with this, right? So, okay, first presentation of the second day. Yesterday, the bar was set very high. So today we'll try to keep up with the quality of the presentations, and I hope that we have as interesting conversations and learnings as we had yesterday. My name is Joseba Ormachea, and I come from Tecnalia. Tecnalia is a research and development center from the north of Spain, in the Basque Country. I guess many of you will know about it, so I won't go very deep into its presentation. Today, I will present our work in the development and application of new extended stress sequences to characterize the durability of BIPV modules. During this presentation, first of all, I will go through the context in which this work has been carried out. That is the Misery European project. I will explain you a little bit the pilot measurement and verification line number 1 that has been conducted by Tecnalia in this project, and I will explain you the details about the new extended stress sequences that have been developed, and I will show you some clear application in innovative BIPV solutions and the results that we obtained from this application, and I will finalize my presentation with some concluding remarks or some take-home messages. So, the Misery project is a European project aiming to create a distributed open innovation ecosystem to boost inclusive change in the building sector. For that purpose, it has different scopes of action. First of all, it tries to develop near zero energy building solutions for the envelopes of the buildings. It tries to transfer knowledge between different stakeholders of this sector, and to match the testing needs of the different actors with the testing facilities that are available in the centers nowadays. It also provides services for the monitorization of the performance of these solutions in living labs, and it also tries to standardize the new building solutions that are developed between the different stakeholders, both the small and medium enterprises and the larger industries. And for that purpose, Misery basically offers a new single entry point virtual marketplace based on 9 different pilot and measurement and verification lines and 3 open innovation services that cover training, business model development, and generation of IP and knowledge. Tecnalia has been mostly working on the pilot measurement and verification line, which aims at the building integrated products that are photovoltaic devices, solar thermal devices, and hybrid photovoltaic and thermal devices. And basically, it tries to characterize how the coupled effects or the environmental effects from the building environment affect the efficiency and safety that are required from these components. For that purpose, it has developed new testing methods that you can see listed there. For example, a new dynamic wind load test using a great fan, also a great scale calorimetric hood to see how the products react in front of fire. Also a coupled fire electric test to see how the products or the new envelope systems react in front of this coupled hazard. Also an optical evaluation for, okay, the line there has changed a little bit when they created this presentation, but the underlying part should be the new extended stress test sequences, which is the part that I will go more in depth in this presentation. Also an optical evaluation method for varying incident angle in the devices, and a service for the performance of the characterization of the real energy yield that the solutions offer in the buildings. All right. In this presentation, I will mostly work on the development of new extended stress sequences. Our goal was to develop new sequences for BIPV modules that will guarantee their long-term durability in the building environment. The thing is that we saw that there are many standards nowadays for PV modules, but none of them guarantee the long-term durability in the building environment. There is, of course, the IEC 61215, which is the mainstream or most used standard for PV modules, but it doesn't guarantee the long-term reliability of the modules in all environments. And for example, a new technical specification, the 63209, proposes a long-term performance testing sequence, but this is meant only for ground-mounted PV modules, and it doesn't cover the BIPV modules. There is also the IEC 63092, which introduces some requirements for building integrated photovoltaic devices, but there is no specification or standard that covers the long-term durability of BIPV modules. Therefore, we see a need here to develop long-term performance testing sequences for BIPV products. And based on the three standards that I mentioned before, and the ISO 12543, which is meant for building integrated glass, we developed three new sequences that you can see listed below: the mechanical stresses and environmental action sequence, the thermal fatigue sequence, and the combined UV and thermal fatigue sequence. First of all, I will explain you the mechanical stresses and environmental aging action sequence. This sequence is in itself divided into three subsequences, and the samples that are used will undergo all subsequences. They all start with a damp heat for 1,000 hours, and they finish with a thermal cycling for 50 cycles and a humidity freeze test for 10 cycles. But then in between, they have different mechanical tests. In one of the subsequences, there is the dynamic wind load test, the new test that has been developed, and a hail test with the impact of steel balls. In another of the subsequences, only the wind test is performed, and in the other subsequence, no mechanical test is performed. This sequence is based on those standards that you can see there, and after and before each test, different intermediate characterizations are performed. For example, the visual inspection of the samples, the recording of IV curves, the insulation testing, wet leakage testing, and electroluminescence imaging. And the performance of this sequence would take around 2 months. Here you can see the test setup for the new dynamic wind load test, which basically consists of a big fan and some samples in a rack in front of them, and an ever-increasing wind speed and wind load is applied in the samples during this test. In the thermal fatigue sequence is basically the sequence one of IEC technical standard 63209, but with performing intermediate characterizations every 200 cycles, and the development of this sequence would take around 2.5 months. Finally, the combined UV and thermal fatigue sequence, again, is divided in three subsequences. They all start with a damp heat for 200 hours, and they finish with a thermal cycling for 150 cycles and a humidity freeze test for 30 cycles, but they have different intermediate steps. In one of the subsequences, a high temperature test is performed. In another one, a high humidity test. And in the last one, a very strong UV radiation test is performed. By covering these subsequences, the samples would succeed in performing in the sequence 3 of ISE Technical Standard 63209 and the ISO 12543 for building laminated glass. And this is the longest sequence, and it takes about around 4.5 months to perform. So these new sequences have been applied in 3 innovative BIPV modules. One of them I won't be able to show you the results of because the manufacturer wants to keep them secret for now, but I will be able to show you the results in the FlexBrick BIPV modules and also in the composite BIPV modules developed in-house by Tecnalia. And then the sequences were also applied in conventional glass PV modules as references. In general, in the FlexBrick BIPV modules, we saw that the modules performed pretty well in the mechanical stresses and environmental actions sequence. They didn't show a lot of variation in the electrical parameters, and they also saw fracture due to the hail impact at 7 joules, but they survived pretty well the 2 joule impact. Regarding the composite PV modules, in the thermal fatigue sequence, they performed pretty well without strong variations in the PV parameters. Only there was one outlier, and that was our mistake, because during the characterization, one of the connections was broken, affecting the fill factor and the power output. But in the combined UV and thermal fatigue sequence, we did see a strong decline in power performance in only one of the subsequences, and that was in the subsequence containing the UV test. Here we can see how the samples performed during this sequence, and we can see that in the subsequence containing the UV test, after the final humidity freeze test, a strong coloration of the sample was observed. And this shows that the couple effects are very important in this kind of sequences, and that the intermediate characterizations are important to take into. Finally, the glass PV modules performed pretty well in all of the sequences, and we didn't see any strong variations. So in conclusion, 3 new extended stress sequences have been developed and applied, and this enabled testing for long-term reliability of the BIPV modules. The sequences may seem a little bit harsh in the beginning, but most of the modules performed pretty well in them, and they survived them quite well. The thermal fatigue sequence resulted to be very mild because the modules didn't show any strong variation. But the UV exposure in the combined UV and thermal fatigue sequence resulted to be very severe for some of the samples. All the tested samples withstood the new dynamic wind test without any problem, and in general, the whole mechanical and environmental aging sequence as well. And in some of the sequences, we did see some combined effect, so it is important to perform intermediate characterization from one test to the other. And in general, we saw that these sequences give important information about the reliability and the possible design improvements that are applicable in these BIPV modules. So this has been my presentation. Thank you very much for your attention, and I will be open to answer any question now or later in the chat.
Thank you very much, Joseba. Very nice presentation. You tackled one of the main challenges we have to bring BIPV into the market, to combine the electrical safety certification scheme and test with the construction product regulation test. I do have several questions, but I will ask you only one. What are the pass and fail criteria in these different tests? And what happens if I change the dimension, for example, of the module? Do I have to undergo again these tests, or it's something that can be avoided?
In general, we develop these sequences, and we design them so that there wouldn't be any pass or fail criteria in the beginning. So the idea of this test is that we see how the modules perform in front of different couple effects, but we didn't set any pass or fail criteria in general. So they would be used just to evaluate how the modules perform in front of different couple effects, and we would usually go through the whole test.
Good. Thank you. Thank you very much, Joseba. Thanks again.
Well, second intervention of the day, Jens Morschner from Q Leuven. He will give us a presentation about advanced electrical integration of PV into building systems. The floor is yours.
Thank you very much. Good morning, everybody. Question is, how do I dare coming to an IPV conference without anything about PV really, or fancy panels? The reason is that this is about something else. And that is an aspect that, in my view, is a bit undervalued in all the development of building integrated PV, and that is the electrical integration. First, I want to say where we're coming from. This is Genk in Belgium, a campus that is called Torpark, which is an old mine site, and is turned into a living lab, really, with a lot of installations. So you see 2 buildings of Energyville in the front. You see some demo buildings on the right. It has a training center. It has startup companies. It has, not least, also the factory of Soltech. And in the research part, we're working with 4 partners. So that is KU Leuven, that is Vito, Flemish Research Center, that is IMEC as the Electronics Research Center, and the University of Hasselt. We're collaborating on everything around the energy transition, from battery materials to grid planning and everything in between. So what do you want to do? Zero energy buildings, that was mentioned in the previous talk. Thank you very much. That's, of course, where we need to head to. Or if we talk about renovation, then maybe more near zero energy buildings. The ratio of renovation to new construction is a bit a matter of debate, but it is safe to say that out of the buildings that will exist in 2050, most have already been built. So it's sort of an 80-20 relation, maybe 75-25. And if you want to go towards zero energy, then of course you need integration of PV. And that also means you need to get PV into the value chain of buildings. And that is something where we haven't really arrived yet. So PV is still treated as a specialty that needs special planning and special sales channels and everything. It's not like a building component like every other. So there's work to do, I guess. That's not so much for university. But what we can serve is to make that technically easier, and that's what we want to do. So what does a building owner need? He needs PV generation, obviously an energy management system, and then an optimization for self-sufficiency and self-consumption of the produced electricity. So buildings will really become active units in the energy system, and they will also participate in the energy market, meaning extra money or reduction of costs, whichever way you want to see that. And you obviously want to do that in an automated fashion, not manually. So effective BIPV integration needs advanced electrical integration. Some comment on the challenges. For the building integration, well, I don't need to explain to you that that is complex. You have all these players in the value chain that need to work together. You have a mechanical problem to solve and an electrical one, contrary to most other building components. You need to plan this together so that it really becomes a unit in the building. Then you're not producing electricity anymore for grid injection. That's of low value. You would not build PV systems for that, certainly not expensive ones in a building. You want to have flexibility as much as you can to play with. And also more and more we see grid constraints that we need to address when managing energy. Then we need to also be prepared for a changing environment, meaning this is gradually adopted. We see this changing. We see PV, then we add storage, EVs will certainly be added. We see more heat pump heating and so forth. And not least, also the requirements of the grid are being tightened. So we're looking for an approach that actually helps integrate all of this into future buildings. Oops, something happened with this slide, I don't know. Okay, good. So, but I mean, I'm preaching to the choir here, so I don't have to explain that usually rooftops are insufficient to produce enough electricity, that you see partial shading, especially if you look at facades. We saw some examples yesterday. Then you have PV panels of different sizes and different time profiles, orientations, and ideally in such a system, when you install, you would not need an electrician. This image, by the way, does not have PV, so I just stole that from a partner of ours, Build Up. And they're prefabricating elements for the renovation of buildings. So their building is scanned, then elements are produced and then installed at the building. The problem is actually that you have to have an electrician on standby to wire this up while it is being installed. And in an ideal world, you would have integrated smart converters in these building elements, and they would have a plug so that anybody can plug this together. That would be the vision. A bit closer on what that could look like. Oops, something happened to my slides, I'm sorry. But yeah, so you would have your converters integrated. They should be plug and play ready, so they should have all the communication needed, all the interfacing built in. So you connect them readily to a power bus. And the converter should do the adaptation. So not that you have to think like which modules do I wire together, which other ones to produce the same power and so forth. So the adaptation to variations in orientation and so forth, that should actually be covered by the converter. Then, yeah, you need communication. Ideally, that would also feed into a learning system, so the converter can actually support forecasting of how much will be produced. And then, yeah, yes, you have a bus connection that brings this all together. Unfortunately, my animation has disappeared here also. So the other point is, do we want this in DC? And DC has various advantages. So you can reduce the electric losses. You can also achieve that with simpler converters. You can have a building internal system that is actually independent of the grid, meaning you can control it separately. You're not under all the requirements that the grid connection has. You can increase the operational security. You can even keep this running for backup, or at least parts of it, in case the grid is out. And you only have one interface that needs to fulfill all the requirements of the grid. And that should eventually also lead to cost advantages. And the grid requirements, not least, they will be increasing. So, I mean, we heard about the difficulties with grid stability in the event that there are less and less synchronous generators, as is increasingly the case with more renewables being deployed. So, grid stabilization is an issue, virtual inertia, and also write-through capabilities, but also dealing with curtailment that you see in grid feeders that needs to be managed. And if you want to get to such a system, then you want to base that on open standards. There are proprietary systems already that you can buy, but I think in order to deploy this widely, we need open standards to make this succeed. Okay, I'm closing with a map. This has also been a bit bent. So we need the PV in the building elements, obviously. We need the smart converters. We need to tie them to a smart electrical system. And then there are lots of ins and outs that I don't want to go through. The ones highlighted in blue are ones that we're in principle already addressing. And then there are a lot of more ideas that we're happy to cover with partners. So I hope this triggers ideas in you, and we'd love to hear them. Lastly, thank you for your attention. I'm showing the demo buildings that we're currently building on the Tor campus. The one on the left is called Constructor. It has a new part and parts that actually build like old buildings and will be renovated. And then two on the right side that are called Toriak, where you can do A/B testing right in those buildings. Also there, if we can use this to support any of you, please approach us. Thank you very much.
Thank you very much, Jens. Very interesting also because this is often an overlooked problem in the PV industry anyhow. And you addressed and you mentioned a point that I found very important, and like several events over the last months proved it. The grid is often a problem of ours in Europe, but not just. So first, do you see any of the intervention of the European institutions in the sense being able somehow to solve some of the problems that you mentioned, first? And second, Do you think that storage could be sort of an instrument or a tool that could address also some integration issues that some buildings might have?
Yes, well, to maybe answer the second question first, storage is definitely needed. So if you need a building that can actually manage its energy, then flexibilization of load goes so far, but then storage is a very important component in that indeed, especially, well, you know, with the, when PV is generated and when you need most of the energy. It depends on the type of building. I did not talk about which type of buildings we would be addressing, but we're thinking more like larger buildings, not small residential, or larger residential and also commercial buildings. So yes, definitely storage is part of the game. And the prices have come down a lot, so it's feasibility. Then on the institutional question, I'm not sure what to say. I think it's, if I see the upcoming Horizon calls, it's not directly head-on addressed, so you can like put in parts of that into proposals, but it's not like a core topic that would be striking. I think that is maybe a, should be a goal. Also, if I see IAA PVPS, you have the tasks 13 and 15, which are doing great jobs on performance and building integration, and you have 19 now on all the grid aspects. But for me, there's somehow still a gap between those that could be addressed better.
Thank you. So we are moving to the third speaker of today morning, Alessandro Virtuani from CSEM in Switzerland. We will talk about reliability challenges of BIPV products and system in operation. Alessandro, the floor is yours.
Okay, thanks, Francesco. Okay, just a couple of words about CSEM. CSEM is a public-private innovation center based in Switzerland with an international reach. We have a sustainable energy division, which is mostly PV. We also have activities on batteries, and on PV, we work mostly on solar cells and modules, and integrated PV, which is, of course, BIPV, VIPV, and several other activities. We are also a member of the Seamless project organizing this conference, and you will also hear another presentation from my colleague Lison in the next session. Now, this is a general classification of BIPV. So when we talk about PV in buildings, which is maybe the correct expression, we generally encompass different types of applications. So you see it here on the top row, we have a building applied, and we have different, so residential, industrial, and heritage installations. And basically, it's when we apply a PV module, a PV system on top, for example, of an existing roof. So the building element is already there, and it's not replacing it. Whereas for a really purely building integrated, the PV system or the PV modules are replacing building components, so they are effectively integrated into the building envelope, so as in the bottom row. So what about the reliability of the installation in the building context? We have this nice picture drafted by Ugo Quest, a PhD student, and which summarizes a little bit of the challenges that these modules are facing. So for sure, PV in the built environment is experiencing harsher operating conditions compared to so-called open rack or ventilated PV modules like grounded PV modules. And for sure, there are some additional stresses due to the thermal and higher thermomechanical stresses. We will see something about this. Another issue is the frequent exposure to shading. So a built environment is much more prone to the presence of shading, also much more frequent shading than for open rack mounted modules very often. And of course, there can be other issues like the soiling, snow coverage, and soiling. Another issue, which is maybe not captured by this picture, by this very informative picture, is that, for example, if we are using solar roof tiles, very often we have a high number of connectors, long cables, and the duplications of connectors and also bypass diodes. And of course, the more we increase the connectors and the number of bypass diodes, potentially we are also weakening the system. Now, what happens, for example, with some of these failure modes? I mean, I think you do not read it here. I changed the color, but it's changed again. So, of course, for example, the exposure to shading can lead to high operating temperature of some specific solar cells, the one which are shaded, and this will generate some overheating, what is called hotspot, which might in turn lead to the generation of other phenomena. So very often we all agree that operation in the built environment poses some challenges, not just in terms of performance or energy yield, but also in terms of long-term performance, so reliability and lifetime. But so far, I think we just came out with some qualitative assessment, whereas in the last couple of years, we have been working at, I had the pleasure to supervise a pool of PhD students and postdocs, so we have published several contributions at conferences or works, and it was the first time for me to really sit around the table and try to have a look at this and see what we learned in the couple of years. So having said this was a very long premise, so I will go quite quickly. So there's also a change in this slide, but so if we have a look at these results, which is a test stand which was developed and monitored at SUPSI in Lugano, you see that this is temperature, this is probability density of BIPV versus open rack modules, and we see, and this is the last bar here, something is changed there, but you can see that if we have a look at the maximum temperature, which is the last column, we see that, that we can have this temperature difference of up to 26, between 20 and nearly 30 degrees for the operation for us fully insulated modules compared to an open rack module. This is already an interesting information, nothing new, but we have captured it for several different years. So this is statistic averaged over, I think, 4 years of data at least. And what is the effect of temperature? So on the same test stand, this is another work published by Ebrar Ochalai. And this is on the left-hand side, you see after 51 months of operation, this is the indoor measured power of modules that were deployed open rack, so fully ventilated, and in a BIPV mode, fully insulated. And you see that if we have a look at the first data, the maximum power, we see that there is a considerable power loss for the integrated PV modules by 3% compared to the 0.27% of the open rack module. So there is really effect of temperature, and we also tried it maybe for one of the first times to explain it. So there were some characterization of the polymers performed at OFI in Vienna, and you can see it here. So this is UV fluorescence analysis, which is an imaging technique. And we have these two pictures, and the first one is the open rack module, which you get a kind of pattern, and this is the insulated module. So you see a completely different partner. Basically for UV fluorescence, you illuminate the module with UV source, and then you take a picture, and you have this fluorescence phenomena for EVA and sometimes also for other polymers. And you see that the higher signal corresponds to a higher fluorescence, which can be linked to a degradation of the polymer. We also perform some UV fluorescence spectroscopy, but I do not have time to discuss this. You can see, maybe it's difficult to see, but there is some strong browning over the center of the cell. Maybe another... Okay, this is also a complicated one, but you can imagine that we have, for sure, if we refer to temperatures, we have intraday variation, so maximum variation in the module temperature between night and day, so very strong cycles. And the intraday temperature variation will be much higher for BIPV modules, so fully integrated. But we were also taking the different perspective at looking at intradaily temperature variation. So you can have a snow cover, you can have clouds passing by, so a sudden drop in the temperature, which is going back. And during the day, you just do not just have diurnal variations, but really intraday variation of the temperatures. And we were adopting this temperature travel metrics, which I think we never was using before in PV, but is used by other industries. And basically it's captured by these figures. So this was a mock-up setup we installed at EPFL before COVID times, where we were simulating different typologies of insulation. So insulated, closed roof, basically BIPV, and open rack, and different inclinations. And the results are captured here. So if you have a look at the chart in the middle, you have the temperature traveled, which is basically the cumulative sum of this temperature difference over a full year. And so the higher the temperature traveled, the higher the variations in temperature. And you can see it in the central figure for the 45 degrees tilt mock-up. We have results for the open rack, for the closed roof, and for the insulated. And basically, there is a very slight difference between closed roof, BIPV, and fully insulated. But if you have a look, for example, at the horizontal installation or the facade installation, you see that the closed roof is basically traveling a higher temperature. So this was, I mean, if we think at it, it's not completely unexpected, but it was a surprise to us. And potentially, this temperature travel could be translated to a higher stress or fatigue on the solder joints. So they could really, on the long term, be affected by a higher degradation, which might lead to an increased area resistance and a lower fill factor. So lower performance after all. I think I would have quite other material, but I will try to close it here. So compared to 20 years ago when we were working on the topic, at the time there were basically no standards for BIPV. There were the typical standard for the reliability and performance of and safety for PV modules. But at the time we were identifying a lot of missing gaps to account for this operation under harsher climatic conditions. In these 20 years, a lot of work has been done, as it was also mentioned in the previous presentation. And I think that from the BIPV industry, we can really learn, since we have at least much more experience than for other integrated PV industries like BIPV or Agri-PV. And I will maybe wrap it here. Well, I do not have time, but I think that for sure we have a higher operating temperature for full integration. We have a higher temperature traveled, which transfers on higher stress and fatigue on solder joint. I did not have time to talk too much about frequent shading, but of course you can imagine that frequent shading is stressing the bypass diodes. And bypass diodes increase the risk of hotspot occurrence, which can consequently bring to the occurrence of several other different degradation mechanisms. And particularly if you have defective bypass diodes or solder joints, there is a potential and higher risk of arching. And this opens up the topic of overheating and fire threat, which I'm not touching today. Thank you for your attention.
Thank you very much, Alessandro. You had a really tough job to speak about reliability and different case studies for BIPV in only 10 minutes, but I think you gave a really nice overview of the main problem that a BIPV system can have. I have a bit of a provocative question because we see that there are many harsher conditions for BIPV in comparison with conventional PV system. But now we do have BIPV installation, BIPV examples running since more than 10 years, even 20 years. Have you found any, or how many issues you have found in real projects? So is there really a problem of reliability of BIPV considering real case studies, or the manufacturing are so good in making tests and providing good technology that these are potential problems, but in reality, the case studies with this kind of problem are not so many?
Difficult question. I would say that for sure we see a lot of, shading, frequent shading is an issue. You see it, you take thermography pictures and you see it, and in the long term it can really solicitate the diodes and make them blow. So at some point the modules will not be protected any longer. For the long-term degradation of the polymers, which can be correlated or to the higher operating temperatures, we see yellowing of laminates and this kind of thing. So I think there is an impact, but we really need to look at the data, and it's difficult to access the data sometimes. I think there is a question from
Yeah, maybe, yes, I will come back to you. So maybe a message could be, if the design is properly done and considering the right technology, then this reliability point may not occur.
I think good design of the PV module, which is something very difficult these days, particularly for mainstream products, and good design of the PV system.
Yeah. Thanks.
So it's professional who need to do the job.
Yeah, thanks. Yeah, maybe we have time for one question. Yeah, okay, we may take it for the end of the session. Yes, thanks.
Thank you so much. Next person to take the floor is going to be Eleonora Tomasino from URAC Research. She will give a presentation about UV-induced degradation on vertical PV installations. Eleonora, the floor is yours.
Yeah. Thank you. First of all, it was a pleasure for me to be here. So today I will talk about my current research work that is focused on the study of the impact of UV-induced degradation on vertical BIPV installations. And in particular, the first part of this study that I'm going to present you today will talk about the main the difference of stress factors incident on vertical versus optimally tilted installations. So why this topic? First of all, as you all know, PV modules are exposed to decades of UV radiation, which in particular the UVB fraction is very detrimental for the constituent materials of the modules, as they initiate several degradation processes such as the yellowing and the delamination of the encapsulant, the chalking of the backsheet, and the degradation of the cell itself. Moreover, recent studies also proved that the novel N-type solar cells are very sensitive to this kind of degradation. And this is due to the particular conformation of their front passivation layer. To conclude, there are also novel materials, such as novel encapsulant with the low UV cutoff, that are emerging in the market and which promise to get much higher energy yields. So, as you can imagine, the deployment of these two types of material is in contrast to each other. So in order to also face a bit the lack of research and standardization on this topic, there are several studies that are focused on the effect of the different climatic conditions on the degradation of the PV modules. However, at least based on our knowledge, there is almost no research that instead study the effect of different inclinations and orientations. So on the other side, we believe that it is very important to analyze also these more in details, these vertical installations, as they are emerging, in particular in the BIPV field. So the aim of this research was to try to fulfill the existing research gap by, first of all, estimating what is the impact of these stress factors. And I don't talk only about UV, but also the temperature of the module for vertical installations, and then trying to correlate the experimental determined degradation rates with these outdoor conditions. So the final goal in the end would be to demonstrate also the potential adoption of these novel materials for vertical BIPV. So for the first part of the analysis, as I said, we have simulated the incident, the total and UV irradiance incident on surfaces in different case studies, as I will show later. And in order to do this, we have used the radiative transfer model, SMARTS, which, let's say, compared to traditional estimation that consider just 5% consider that the UV irradiance is 5% of the total irradiance. In this way, we are also able to consider all the atmospheric parameters and also, for instance, the effect of the albedo of the surrounding environment that are also very important. So for the first analysis, we have considered 3 representative locations in Italy, which are Lampedusa, analyzed once with the grass albedo and once with the concrete albedo, then Bolzano, that is representative of the continental zone, and finally Mount Viotz, that instead is representative of alpine environment, and this location in particular is characterized also by the snow albedo for, I think, 6 months of the year. So for each case study, we have calculated the annual, total, and the UV irradiance incident on horizontal, tilted, and vertical surfaces with different orientations. As you can see from the graph, we can notice that there is a very big difference of especially UV irradiance when comparing vertical against optimally tilted surfaces. This difference was a bit lower in the case of the alpine environment, as expected. This is due to both a decrease of air mass and also because of the effect of the snow albedo. However, even when considering the worst case, that is the alpine environment during the winter season, even though the total irradiance incident on vertical surfaces was a bit higher, if we zoom in the solar spectrum and we look only the fraction of UVB, we can see that this is always lower for vertical facades. So we can say that we are in safer conditions. Then, of course, not only the radiation, but also the temperature of the module can be affected by the particular position. So we have estimated it by using the Sandia model, which expresses the temperature of the module as a function of the plane of array radiance, and then the wind speed and the ambient temperature of the specific location. But it is also strongly dependent on the installation configuration. So we have analyzed, in particular, 2 case studies that are open rack, so ventilated back of the module, and closed mount, so insulated or low ventilation behind the module. So as you can see from the graph, we can observe that when considering the same mounting configuration, the temperature of vertical modules was lower than the one of tilted modules during the summer months, while it was equal or slightly higher during the winter months. So following this first theoretical study, we have also started to conduct some preliminary tests on 4 mini modules that were laminated in the EURAC laboratories. And these were subjected to UV aging inside the UV chamber for a total UV dose at the moment of 62 kilowatt-hour per square meter. And we have calculated the degradation rates by monitoring the loss in maximum power. And then in order to correlate these degradation rates with the finding of the outdoor conditions, I have calculated the equivalent years of exposure, which means the total number of years that are required in order to reach the same amount of UV dose as the experimental dose. And finally, in a very simplified approach, I would say, I have translated the hourly based degradation rate found with the experiment into orientation and location specific annual degradation rates. As we can see, there was a significant, I would say, not negligible, at least variation of degradation rate, especially when considering more sensitive modules. So in this case, I just plotted 2 best modules. And so the main takeaway, so what we can conclude from this first analysis is that there was actually a great influence of module inclination and also orientation on the incident UV irradiance. And also there was some impact on module's temperature, even though this is mostly affected by the installation configuration. And together, these two stress factors can have also significant impact on the final UV-induced degradation effects. As next step, we plan also to improve the study by considering combined stress factors, so combining the effect of temperature and UV radiance, and this can be done by calculating the acceleration factor that is specific for given module materials and also for a specific degradation mechanism. And just we want to prove, what we want to prove is that it could be possible to use some materials that are generally considered unsuitable in classical PV installation due to their high sensitivity to UV. They could be instead viable for vertical BIPV applications, so paving the way for the new design opportunities which help to improve the energy yield without compromising the durability. That's all from my side. Thank you.
Thank you, Eleonora, for the nice presentation. I didn't get really the impact of the albedo and of the surrounding on your studies. Can you repeat a bit?
Yeah, of course. The albedo is a big fraction that maybe generally is not very considered, particularly for tilted and horizontal modules, because it's not affecting. But for vertical installation, it is very important indeed. We have also done this simulation by varying the albedo to see the impact. For instance, in the case that I showed for Lampedusa, we have considered once the grass albedo and once the concrete. In that case, there was no significant variation because let's say the effect of these two surrounding material was similar. So I think just the grass has a bit more of reflection, so more radiation that is finally reaching the surface. Instead, there was a very big effect of the snow albedo. As you can imagine, the snow is reflecting more light, so a lot of the amount of light that was reaching the vertical surface in the alpine environment was due to the effect of the albedo. So yes.
Thank you. Thank you very much, Eleonora, again, for your presentation. Good. We are moving now to the fifth presentation from Claire Morin from Solar Power Europe in Belgium. She will tackle a very hot topic. Indeed, she will speak about fireproofing BIPV, overview and comparison of building fire safety regulation in increased demonstration site countries. Claire, the floor is yours.
Yeah, thank you. Good morning, everybody. So now we're looking into something a bit different. So it's really building regulations and how the fire safety requirements for building components impact the deployment of BIPV on those buildings. But first, just a few words about the INCREASE project, because this paper was developed in the context of INCREASE. So it's an EU-funded project that focuses on module and system innovation, but also looks at improving the enabling environment for IPV. So looking at regulations, stakeholder engagement, and standardization activities. So here you have an overview of all the partners, but then I will just go into the paper. So first, yes, the European Framework for Construction Products. So in the EU, you have the Construction Product Regulation that applies to all the member states, and that provides a classification that applies to all member states, as I said. So a classification on the fire behavior of construction product components. So this is based on the standard EN 13501. And with this, you have a classification going from Euroclass A1, so non-combustible, to F, which is very combustible. So on the one hand, we have this classification. And then on the second hand, we have every EU member state that decide, okay, on which building we need which kind of fire safety requirements. And those decisions are made in every member state. So you have different rules. But what does that mean for BIPV? So in practice, when you do the testing on BIPV elements according to the standard EN 13501, BIPV element can only reach Euroclass B. So that means in practice that if in the regulation a country asks for, let's say, A class on a certain type of building, in practice, you're not allowed to install BIPV on this building because it cannot reach the A class. So in the paper, we look at the 5 countries where INCREASE has demonstration sites. So it's Belgium, Estonia, France, Spain, and Switzerland. We also have Montenegro, but I've put it aside because it's not so easy to find information on their regulations. So in the paper, we look at building classification, requirements for facade elements, but also for roofs. And then we do a comparative analysis. Based on this, we have some policy recommendation. So we'll just go directly into the analysis of the regulatory frameworks. So we have 2 trends that are common across all the member states all the countries that were studied. So since 2017 and the Grenfell Tower fire, there has been updates, or currently there are updates in the regulations. And in those updates, you have stronger fire safety requirements for building components, especially for high-rise buildings. And then in all those countries, the higher the building, the higher the fire safety requirements. So you need higher Euro classes in high-rise buildings. But then how are those fire safety requirements determined? In most countries, it's just based on height. So like in Belgium, Spain, and Switzerland. So the higher the building, the higher the requirements. Or you can have a mix of use and of the building and height of the building, like it's the case in France and in Estonia. And especially in France, it really stands out because you have a specific regulation for residential building and a specific one for non-residential. And then within those categories, you have subclasses, and each non-residential, unresidential buildings have their own thresholds in terms of fire safety requirements. So in practice, in all, EU member states, but also in Switzerland, you can use the Euro classes. But in Switzerland, there is also another system of classification because it's not an EU member state. And then in France, in practice, only Euro classes are accepted, but in the regulation, you still have the old system. So it's a bit confusing, but you have to use Euro classes nowadays. Then something also quite interesting in Switzerland, among all the countries' studies, they have created, so the Solar PV Association has created guidelines to support the planning and the assessment of the fire safety of BIPV integrated in ventilated facades for mid-rise and high-rise buildings. So it's really, those guidelines are really helpful to support the deployment of BIPV in mid-rise and high-rise buildings. And then a last element that can allow to deploy BIPV when the regulation doesn't allow it is that in Belgium you can go for large-scale fire facade testing that you can use in case the regulation doesn't allow to put BIPV because the Euroclass requirements are too high. So in France, also in practice, you can have laboratory assessments for BIPV elements, but it's project specific, it's timely, costly, and you're actually not sure that your assessment will be validated. So you can have those assessments, but they're mainly for very flagship or prestige projects that can absorb the costs and delays. So yes, I will not go into details, but when you look at the requirements, so for roofs, you have different requirements, but they're not an issue for BIPV deployment. So I will just leave them a bit aside. And then, well, in every country, for low rise, you're allowed to put, let's say, lower Euro classes in your components, and then the higher the building, the higher the requirements. And then in some cases, if you need A2, well, if the regulation asks for A2 building elements, then you just cannot put BIPV if you follow the regulation. So based on these observations, we can make a typology of sorts of BIPV projects. So there are with 4 categories, and they would be based on heights, so low-rise, mid-rise, and high-rise, but also high-risk buildings. So those are like such as welfare buildings, like hospitals, or education buildings that in some cases, they have also more stringent requirements. So I would also put them in a separate category. It's not always the case, but it's something that's seen. And then, yes, so as I said, the lower the building, the more BIPV friendly, in a way, the requirements. And then, so if you allow, we see in the regulations that if you allow for a sort of alternative pathway to show that your BIPV product is safe in terms of fire, the feasibility of putting BIPV in a building increases. So it can be testing or also having the guidelines like in Switzerland. And so based on this, we have 5 policy recommendations. So harmonize the BIPV standards at European level. So really, since BIPV has to comply with both construction and electrotechnical requirements, it's not really helpful and hindering the deployment of BIPV. So we need a unified European approach to streamline compliance. Number 2, introduce performance-based compliance pathways. So in that case, like such as having fire testing at large scales for BIPV facade and so on. So this should be in the regulation, but also in practice, it should work, unlike in some countries. Then third, developing BIPV-specific fire testing methodologies, because in the current standards, they're based, of course, on building products, so they're not actually adapted to BIPV elements. So, for instance, BIPV may remain electrically active during a fire, and this is not tested in EN 13501, for instance, or something that's not also addressed is how the fire evolves in the facade. So this would be for facades, but also for roofs, there are also some tests that need to be more specific, because with the current test, they only assess a fire that comes from an external source, but not from inside. So it doesn't take into account that the fire might come from the BIPV roof. And then 4, establish clear national guidelines to bridge the regulatory gap. So the idea here would be to really take Switzerland as a good practice and, let's say, support that other member states develop such guidelines that can help bridge the gap in the regulation. And then number 5, support further research and data sharing. So the idea is really to keep researching on the fire behavior of BIPV system, especially under operational condition. And this will be crucial to inform the future standards and ensure that BIPV can be deployed in as many buildings as possible. And thank you.
Claire, I will have a question for you. So basically, you mentioned that as a first policy recommendation, you would like the European institution to harmonize the standards at a European level. And this is quite relevant because also operators can work also in different environments in different countries without creating additional knowledge, and this is quite relevant. But how long would it take just to harmonize standards? Would it be a matter of more than 5 years, or what's your take?
I would hope less than 5 years. It's not really, I'm not such an expert, but I think before there are some means to support BIPV deployment before standardization. So with the guidelines and also with large-scale fire testing, but hopefully it will be faster. Thanks. Yeah.
Maybe just to add one information, just to give you an example of what's happening in Switzerland. In order to develop this national guideline, it took about 3 to 4 years.
Yeah.
So going to on European level, it may take a bit more.
Thanks.
Well, and we are about to close this session with an intervention, a speech from Antonella Trombadori from University of Florence, who will speak about design and solar integration from technical infrastructure to cultural asset in historic contexts. And I think probably she knows something about it, right? I mean, coming from Florence especially.
So good morning. The project is in the framework of an international project, is MEDECOSURE project, involving other partner, other university from the North Africa and Mediterranean country, in order to investigate how it's possible to implement a very good quality and energy reduction in the university building, especially existing building and cultural heritage building. It was a very big challenge because, as you know, the integration of PV is very easier in the new building, but introducing and creating a very good project in the restoration and the rehabilitation of existing building, especially in Florence, in Mediterranean cultural country, under the protection of the Authority of Cultural Building, is a very big challenge. But we start in order to demonstrate how it's possible to implement a pilot project inside the building of university, like a tester, like a pilot project, in order to implement something different, something new, optimizing also the role of university and the research center. I'm the leader of Big Slab, is Building Environmental Experience, in order to promote a new modular, temporary reversibility, and especially pilot project where test the real effect of the PV system, not only to produce energy, but also to implement the quality of the building and to collaborate to optimize the performance and the comfort of the people inside. So first of all, we create a living lab in order to involve not only the university technical office, but also the municipality, many companies, and especially the designer and other researchers around the Europe, in order to optimize the process, optimize the renovation process of the building, and pushing and stressing in order to demonstrate how the PV, again, will support this capacity of the building to have a new performance, a new energy reduction system. And we create, together with the other partner, a new methodology, starting from the knowledge framework of the building, so in order to analyze the criticalities of the building, and then proposing a common co-design process, and implementing a new experimental version of the prototype, and then create a post-management evaluation system in order to monitoring the effect of the pilot, but also involving the end user, and create a communication strategies to optimize the positive behavior of the people, because in that case, the use, but also the awareness of the people inside the building, for us, it's very important. So the priority was, of course, energy efficiency first, but we, as architects, we propose an aesthetical and beauty solution, so demonstrate that also the PV plant are not only a gadget or something that we place on the building only to produce energy, but to integrate, again, the comfort and to ensure the indoor environmental quality of the building, enriching the behavior and enriching also the healthiness of the people inside. During the process of the project, we create a lot of scenarios, starting again from the criticalities, and we understand that the problem was the south facade, we have this kind of laboratory that have a double exposition of the north and south exposition on the ground floor. And the first floor is a teaching room, totally exposed again to the north and the south, so the distribution of the light inside is not homogeneous. So we propose to implement something not inside the envelope of the building, because it's not allowed, but outside. So experimenting how it's possible to use the external place, the near place in between sometimes the building, to contribute with the indirect positive effect of the solution. We introduced some skylight, again, in order to optimize the distribution of the light on the first floor, but we put much more attention to the design of this second skin of the building in order to, optimize the production. So we put more standard panel on the top, but using the amorphous with semi-transparent, with different percentage of semi-transparent, in order to reduce the direct solar gains on the south facade, and in that case, contributing to reduce the cooling needs, so the energy need for the cooling during the summer season. This is the prototype of the structure, and we design an active solar facade. As you can imagine, self-standing, out, not touching the building. It is possible to reuse, maybe in the future. It's a steel structure. We maintain the same architectural proportion of the courtyard that we have. And as I mentioned before, we put on the top the typical monocrystalline panels in order to optimize the production, but in the vertical facade, we propose two different percentages in order to have two different opportunity to maintain the external view from the first floor and the ground floor, but in the same case, testing the production and testing the benefit. In an holistic approach of the design, so pre-intervention and post-intervention, we create a digital twin of the building, and with monitoring still now the real performance of the building, and day by day the CO2 emission, but also the thermal comfort, the thermal flux of the wall, so all the performance of the envelope of the building. And we optimize this, introducing the PV as a collaborative system in order to reduce the glazing, to optimize also the solar facade performance, the natural ventilation also, because in that case we can open the window and obtain a very shadow facade. So at the end, our simulation demonstrate that with this combined design process, we really decrease the energy need much more than 50%. It was not so easy to create the infrastructure, because the working place during the summer season was not allowed to the student, but we need also a very technological solution to implement the pilot. So we need to design this kind of structured modular structure, allowing a very easy solution, but maintaining a very good weight of the steel structure. So it was also very interesting to analyze the process of building in an existing real building, real state. And this is the panel when I arrived. So it was very important, the dialogue with the company, and thanks to ETA that was in charge to optimize this kind of process and was in charge to select also the best production around Europe. And this is the phase when, with a very interesting, good working worker, it was possible to create the solution. And you see the transparency capacity of the panels. And also we proposed the design, the first solution, we liked to integrate the automation in order to rotate the panels. But the budget was limited. So we proposed to distribute this kind of effect, changing the tilt of the panel, so to the southeast and southwest orientation, in order also to monitor the performance. We create a different grids in order to separate the plan, and we introduce different inverter in order to check and to monitor the performance for each grid. Inside, it was very interesting to monitoring the benefit, direct and indirect benefit, and we elaborate, thanks to the design colleagues, we elaborate an app. So it's possible with the mobile, not only to monitoring the quantity of energy produced day by day, but also it's very important to change the behavior, because in the platform we summarize all the data coming from the light level, the daylight level, the CO2 inside the building, the temperature. So stimulate with an alert the behavior of the people. Very easy, because the alert say the CO2 level is too much, open the door, open the window. So sometimes the solutions are very, very easy if the people are really aware, and the whole building collaborate with all the system, with the facade, with the plant, but also with the behavior of the people inside, to obtain a very good result. The good result, as I mentioned before, much more than 50% of energy saving, much more than 7. Now I'm really pleased to announce that, because this data is a little bit old, we are overcoming the 10 megawatt of kilowatt years produced in 2 years, so much more tons of CO2 emission reduction, a very good quality of visual effect inside, and also we reduce the use of electrical light on the first floor, because thanks to the good average of the light, is also possible to switch on off the light. And we reduce, as I mentioned before, many consumption for the cooling system during the summer. So we suppose that summarize all this kind of benefit, it's much more than the single energy production. And of course, the architectural value, because inside the Faculty of Architecture, we are demonstrating that it's possible to integrate the PV, especially in the facade, especially in existing building, especially in cultural heritage building. This is the prototype of the app, and of course is active. Digital twin combining also with the BIM system to have the real data management. So real simulation, real data, and then the feedback of the people create a very interesting system for us, a very also innovative and experimental project. And we are very, very happy that it's still working and still producing not only energy, but also comfort for people and wellness. Thank you.
Thank you very much, Antonella, for this presentation. I may have a question, yes, for you, because the project is very complex, very interesting. I'm curious to understand how you convinced the owner of the building, the university, to have this kind of second facade on this historical building.
The real answer, or the political answer.
As you want, we can discuss also later.
The real answer was we had the budget to do this. So we collaborate a lot, demonstrate, and selecting when start with the project, because the idea which building we can propose this kind of solution. So the director was really effective and decided, no, we like to have inside the university, but architectural building. So creating this kind of living lab. So the political solution was University of Florence need, and especially architectural need, to demonstrate that we can propose also to the future generation something, and the real experience. So for this, the name of the lab became Building Environmental Experience. So because the student, the researcher, and now the dean changed, the director of technical office is a new one, and especially the problem was the director of Cultural Heritage Authority. Now it's changed, and now everybody are very happy from this prototype and from this. It's only 5 like a prototype. The age, the previous is still 5 here, but they promise that can, yes, great, can maintain like a demonstrator inside the university.
Thanks. Thanks a lot, Antonella.
Well, we are already over time, but if possible, a quick question, starting with Alessandro. If, given climate change and the increase in temperature and a series of social, political, economic trends like urbanization, for instance, of course, we expect perhaps BIPV to be under increased stress over the next years. For instance, do you expect that the delta between BIPV and ground-mounted PV systems, so the difference in temperature might even increase over the 29 degrees threshold that you mentioned before? And then to all the panelists, if they have anything to say about climate change and BIPV safety, for instance, or please just feel free to add.
Well, it's a possibility on the other end, and I maybe did not explicitate it so well before. So I was just showing an example, but we also had examples of PV modules with a different design and a different selection of the material where we could not see, for example, accelerated aging of the polymers. So it's really a matter of very often with polymers, the devil is hidden in the details, which is, for example, the additives you add to the base resin, and then this can really have a very strong impact on the long-term performance of the module. So I think really when we talk about BIPV, we know that there can be some challenges, but it's really a matter of selecting the proper material, of testing the proper materials, of designing the module in a proper way, extending testing sequences for PV modules. And now I just had a quick slide about this, but we really have technical specification that can guide us in testing properly the PV modules for specific application in higher operating temperature, which can be BIPV, but it can also be operation in different climates. And of course, as I mentioned before, also the design, it's very important. I think it's always professional who need to be involved in the process, and you have mitigation strategies to cope with shading and increasing shading. Yeah, in short.
Okay, good. So thanks, Alessandro. We stole some time to the next session, so we don't want to stole some more minutes for the next session. I would like to thanks again all the speakers for being with us, for the nice presentation, and everybody for being here. Coffee break will be after the next session, so stay here. And I would like to welcome here David and Heinz for the next session. So thanks again.
As you can tell, I'm not Gaetan Masson, for those of you who knows Gaetan. As Philip in the first session, he couldn't travel due to strikes in Belgium, so I jumped on a train from our office in Trento to be here and substitute them. Together with Heinz Hosselbrink, we will chair this session. So the session will be structured as following. So the title is Voices from the PV Industry in Europe. We will hear if these voices are strong voices or depressed voices or let's say hopeful voices. We will have 3 speakers. I'm asking the speakers to try to stick on the given time slot, so we have time after the 3 short presentations for questions from us and of course from you. So let's start. The first speaker is Ria Stalder. He's manager of research and innovation at 3S with Solar Solutions, driving innovation in BIPV. He has several years of experience in PV research and industry, and is dedicated to advancing solar architecture and strengthening EU's energy independence. The floor is yours.
Thank you. Thank you for the opportunity to be part of this important discussion about integrated PV for the European industry. I can jump to the next slide. So, okay, normally you would see a video here in the background, but I think it's not possible, unfortunately. 3S, Swiss Solar Solution, who are we? We are a pioneer in the solar industry, especially for BIPV. We were founded in 2001. At that time, we produced laminators and also PV modules with a system to integrate PV into the building, like especially for roof. Now we have 2 manufacturing lines in Switzerland. Oh, now it's working. Great. This is great. With a total capacity of 250 megawatts. So far we have over 25,000 installation, mainly in Switzerland, some in Germany, some in Austria, and very few in Italy, but we really try to push for that market. And maybe you have seen already, we have a booth here. I have my colleague here, Ivano Pola, also from 3S. Please come to us after the presentation or in the break or at lunchtime if you're interested. So we are happy to show you more about our product. Here you see our portfolio nowadays, so no equipment anymore, only modules and system. And our main product is the roof. There we have the module, 4 standard sizes. We have the system to integrate it. Then we have aesthetic options like colors. We have like anti or low glaring solutions. We have also customized module sizes that it's everywhere integratable. And we have nearly the same system also for the Façade. We have a railing solution with some options and also an overhead solution for, as example, carports, entrances, and so on. Besides that, we have also services like planning tool, how it's easiest to cover your roof with 3S solution. We have also on-site monitoring, which we provide to customers, and so on. Then I have 3 key messages for you here today. So the goal is to give you a feedback from the industry, a voice from the industry, and one is really the quality. And to realize such installation at Espace Weisshorn, which is around nearly 2,700 meters high, we need high quality. And as we heard before, we have harsh conditions there. UV is a condition, fast and huge changes in the temperature and so on. And that requires a good development, of course, real-world testing, but also mature technology. And we heard that today as well. We cannot just take as example the newest cell technology and then have a fast drop in efficiency or whatever, what we observe as well. As heard, we have more than 20 years in experience and installation, up to even 3,500, even more meters. So it's a real issue. So we need high quality materials and technologies. Beside that, of course, we need high professional people. And it's an issue, I must say. It's not that easy. We need a strong network from supply chain over research partners to the end customer, to installers, whatever. It's really important. And access to capital. So main message here, to summarize, for BIPV is key reliability, also quality, and aesthetics. Then scaling, a very important topic. I think most of us know the pressure on the market. On the one side, China wants to come into the BIPV market in Europe, but beside that, we have many new players also within Europe. So here, again, it's key to sell very good and have a good supply chain. So again, it's about people, having good people. But on the other hand, as we heard, the market is also ready to be enlarged, to be a standard for the building scheme. And therefore, I think it's key to understand the building sector very well. How do they make requirements? How do they make restriction? What they purchase for buildings if they construct them. So we need to listen carefully and be able to adapt to these needs and not dictate too much our requirements. Of course, some requirements we need to push into that, but we cannot do too much. So I think what you hear is we need quite some flexibility for our products to match all the needs from the building sector. So we believe BIPV technology is ready, has matured a lot from this pilot phase over a couple of years. Now it's the time to really go to the standardization of that. And this is a change in the mindset, we believe. So last message here, we need good conditions to have a fruitful market situation. And I think we all know some challenges. And to be interesting for investors, to be interesting for put capital into capex, in machinery and so on. We need to have safe conditions, a good framework. And currently it's a challenge, we see that. As example, we need like a spatial planning, like a secure spatial planning or secure energy policy. But also what needs to be mentioned, there's a asymmetry in the global subsidies. I mean, in China, subsidies are high, in India, in US and within Europe, it's different, but it's also not comparable. So it's somehow, if we want to be autonomy, if we want to have a certain autonomy, we need to have different frameworks. As example, in Italy, we have somehow a tax exemption for special cell types like heterojunction and tandem if they're manufactured in Europe and if they have a certain level of efficiency. So it's a good approach, I think, already, but it's very restricted and limited to certain technologies, and it's not really good also for the full European market, but it's maybe a beginning. So 3S is committed to make the European industry independent, but we need a good frameworks, as you could hear. This, what you see here, is our vision. Make BIPV the new standard for the building envelope. And we invite all of you to be part of this journey. We are happy to collaborate with you in whatever way. Please come to us, we invite you. And with that, maybe see you later at our booth or in discussions. And thank you for your attention.
Thank you very much for the really, really nice presentation and nice visuals. There will be the chance to discuss more about the topics of your presentation. So we leave the questions for after. So the next speaker is Luigi Marras. He's an executive and technology leader with more than 20 years of international experience in PV and advanced materials. He's currently head of technologies at the solar division at Standex International. Previously, he served as a CTO and board member of Coveme, a world leader of polymeric materials, which gave him the chance to work in the PV global ecosystems. He is also CTO and co-founder of Fly Solar Tech Solutions. So, Luigi, the floor is yours.
So, thanks, David, for this kind introduction. I will introduce some innovative technologies that we have developed as a Standex International for integrated photovoltaics and specifically for BIPV. I will start by a short presentation about Standex and its solar projects. I will go more in depth with some specific technologies that we have developed, in particular regarding new materials and design for lightweight PV panels, and some surface functionalization via nanotexture for optical guidance. And I will present some real application as a product in integrated PV, and I will conclude with with a short take-home message. Standex International is a global industry which is active in 5 different segments: electronics, engraving, scientific engineering technologies, and specialty solutions. We have many industrial plants worldwide. 10 of them are in Europe, and 2 specifically focused on engraving, plastic materials, and surface texturing are based in Italy. Just some numbers. Turnover the last fiscal year was in the range of $8,000 million with a good margin of 20%. We are serving different markets: aerospace, medical, industrial, automotive. So you don't see photovoltaics here, but you will see later why this makes sense for us to move in this direction. As a global industry, Standex is innovation in Standex is driven by macro trends. Electrification, of course, is one of the most important, which is booming now. As a consequence, energy demand is exploding. So there is a need for a new way to generate electricity. And the key for this new way is integration. We see integration not only as product integration, so talking about PV embedded into buildings and materials, but integration as a value chain integration. So comprising energy generation, energy distribution, energy management, storage, electronics, materials, manufacturing, so the whole value chain should be integrated. What we see now, there is still an important gap between the 2 important industry. One is the construction industries and the other one is the PV industry. So Standex is trying to develop specific technology to fill this gap. Leveraging the expertise we have in 2 of our core business, one is electronics and the other one is engraving. We focus on 2 important platforms. One is plastics and composites, with specific focus on recyclable plastic and composite for special lightweight, formable, and sustainable design. The other platform is on surface functionalization via optical nanotexture. So regarding recyclable and recycled plastics, we noticed that conventional PV materials are not yet optimized for some architectural application, and at the same time, conventional building materials are not optimized for integrating PV. So we worked a lot on special polymer composites and the engineering of this polymer that are able to combine at the same time lightness, durability, and a full circular design without compromising performances and aesthetics. So it has been a long work done to combine all those different capabilities. Regarding instead optical nanotexture, we developed special hierarchical micro and nanotexture that can trap and drive the light, so enhancing the yield under real world conditions. So to solve the problem of combining at the same time with the surface finishing protection, aesthetics, and high energy yield, especially in non-ideal conditions, which are the main typical condition for integrated PV. We developed the surface texture and we tested and we have been, so the effective behavior of light trapping has been confirmed by on-field tests that are confirmed again in total energy generation. We tested in special vertical application and in other conditions. And important to notice is not only the total energy increased, but which is important for energy management, we avoided peaks, so the distribution of the energy generated was more even and flat. As a real application of our technology, we translated those technologies and idea into real products. We developed these products with some partner, and we certified and validated some of them by cooperating with certifying body like TÜV Fraunhofer. You can see here some example of real products that we have made. Lighting poles, carport, balconies, we made thanks to a cooperation with Fly SolarTech, which is a special manufacturing company in northeast of Italy. And you can see some real application of our the final products, enabling the final products with our technologies for special roofing applications, so curved roof, metal roof, and special design. So to conclude, as a take-home message, integrated PV needs integrated solution. Enabling technologies need enabling partner. So we worked a lot on developing special technologies, but Standex is inviting companies and partners to join this ecosystem and turn enabling technologies into Europe's new solar strength. So that's all. Thank you.
Thank you very much for the interesting presentation. We continue, and it's my pleasure to call Laura Sartore of Ecoprogetti Italy. She's the project manager for the manufacturing solutions. She's also elected chair of the European, ESMC, which is the European Manufacturing Initiative.
Vice chair, yes.
Right. But she's also a living example of how PV knowledge is passed from fathers to daughters. It's your floor.
Thank you very much. Thank you. So thanks, first of all, to ETA Florence and to Stimulus PV for this opportunity. And today I would like to give you an overview of, from the other side, not only from the products, but also from the manufacturing side of all these beautiful products which we are seeing. At Ecoprogetti, what we do, it's producing equipments and machines for PV module manufacturing and recycling. So as they said, actually, the company was founded 30 years ago as a module manufacturer at the very beginning. And then we shifted to machine manufacturing, but our roots are in the module manufacturing. And that's where we come from. We have over 60 gigawatt of installed manufacturing capacity, many countries. Let's say we are an Italian company, but we are really globally oriented and globally focused. We have offices worldwide, India, US, Dubai, of course. And so just a few words about what we do. We have about 180 employees. We are based in Padova. All our production is located in Italy. And we have more than 20 patented technologies in PV. Where we come from? We come from the manufacturing, and one of the first products which we started facing and installing was the BIPV. In 2001, we started with the very early, together also with ETA Florence, the very early applications here in Italy of BIPV. We come from the manufacturing of panels, and that's why we know about raw materials, composition, and what the manufacturer needs to be flexible and to be able to produce this type of beautiful but very challenging products integrated in the buildings. So flexibility and modularity are one of our key values in order to be able to match all these various sizes, colors, textures, and everything. I don't want to talk about gigawatts because we know very well that IPV is going into not gigawatt scale, but mostly square meters. But what we can say is that over all these gigawatts, we have about 20% of PV manufacturing project, between 20 and 30% worldwide. Some examples. We are in Florence, so one of the very first, I know you spoke about that yesterday, one of the very first example was done here in Florence at the Mayer Children's Hospital, where we installed very old panels. I would say panels have already practically 20 years already. So they started in 2005 and 2007. And since then, we kept on building IPV production lines for facade, for roofs, curved, colored, whatever. So I'm trying to give you a roundabout about all the technologies and give you some of our examples of successful projects and what we did to answer the need of the industry. One example, sorry, I crossed the ocean and let's go to North America because this was one of our strongest challenge, I would say. We had to do a fully automatic line capable of changing between 78 different product sizes. 78 different product sizes in a fully automatic mode, not in a manual mode, not in a lab scale mode, but really with complex automation, CPUs, different colors, thickness. And the result was that this very big North America Canadian producer, it was the biggest producer of claddings in the US. They were able to manage this challenge with our equipment. Another example, of course, was the quality control. What to do, how to test all those crazy different shapes where we have to, of course, we have to fill the buildings, but also the quality must be ensured. We've been speaking about quality multiple times today, how to test all those crazy shapes. And here what we try to do is to create flexible tools in order to measure the power of the model, the efficiency with inline quality controls. And not only testing the full panel, but also, of course, the string inspection, the cells inspection, and the matrix before the PV unit is placed on the glass. Another example and challenge, I would say, was with many customers, we faced the need to laminate different technologies and different colored glasses. Not only digital printed, but ceramic coated glasses, inkjet printed glasses, electrochemical glazings as well. We have a lot of customers doing different applications of glasses, different textures in order to match architects' and engineers' needs. So here, what we develop, it's a flexible laminator capable of following and checking and monitoring, let's say, the lamination quality in different measurement points. Another example of flexible automation was our stringer. We have several roof tile producers that use our machines, that use our technologies, and often we're not producing standard, which means that in a panel we have a matrix that is odd, made of odd numbers, made of odd series. So we have to really track with a deep recipe management each and every cell of the panel. Again, inline solar tiles, I really like to give you some view of what is possible to be done with a PV around the industry, because many of those projects and customers are not even know many times. So again, changing between a product to another, it may seem simple, but we have to do it cheap, we have to do it effective, we have to do it efficient in a real production environment, not just in a lab. And that's why we develop auto tool changing for the robots, just like a CNC machine. You set up the recipe of what you want to produce, the drawing of what you want to produce, and the robots auto-tune and auto-adjust to create whatever the idea of the architect was possible. It was that. So another very nice challenge, again, sorry, I bring some example of non-European project, was this huge tile producer. Everybody knows them, or many, let's say, both Tesla and GIF. The Tesla project for us was a real challenge. We had to manufacture one solar tile every 1.6 seconds. So this is bringing IPV to a mass production concept. And that's what we did. We handle with multiple, with device handling multiple tiles at the same time, and with very low cycle time for a production environment running 24/7, so continuous production. Agri-PV, I know you've been speaking yesterday a lot about that. We have several customers in Europe that produce agri-PV with our equipment. Again, it seems simple, but also requires a lot of changeovers, a lot of fine-tuning, and that's why we created a flexible automation, able to play with the different grades of illumination ratios and the shapes that are required for the specific harvest below the panel. Let's not forget, I know we speak a lot about building, but let's not forget flexible. Flexible and lightweight are a big portion of IPV, and we have several customers, for example, DIS in Austria, doing products which are amazing for special applications, and that they basically integrate fiberglass and pre-preg materials inside their panels. Here we had to manufacture a production line for 6-meter long panels, so extremely complex, but the real challenge was how to insulate the panel. So we had to create a laser which was melting the layers together, ensuring the insulation of the panel. BIPV, again, how to produce this BIPV. The big challenge is how to handle a curved glass, how to laminate a curved glass, how to produce it effectively. And this is what we are doing in many of these projects and many of these customers, creating specific customizations inside our equipment to make them able to produce this type of products. I'd like to bring some examples also from Italian companies. Enecom, Solbian are very good customers of us, and they create gorgeous products for the nautical IPV. So flexible and panels integrated inside specific vehicles with, let's say, composite material, not necessarily glass. More standard, of course, I would like not to just to scroll it quickly, but we have customers producing gorgeous products also for IPV integration, not specifically on building facades, but balcony, noise barriers, and carports, canopies. This is possible just by having a flexible automation. So that's what we like to keep in our equipment, a really open, wide possibility to play around. That's it. I just conclude with some special application. You know, PV can be integrated practically everywhere. So we are really used to laminate on tents, on metal substrate, textile, ceramic, marble, anything which you can think, there are industry partners capable of handling it. So I leave you with a bit of our motto, let's solarize every surface. Why? We have the room full of engineers probably and architects. So you need to be aware that it's possible to solarize every surface. At last, let's not forget, sorry, I hope I'm not over time, let's not forget the recycling. Recycling is something new, so I really like that you come and disclose this topic more, maybe with us during the coffee break. We have a unique technology capable of recycling glass-to-glass panels. And that's something since a couple of years new in the market. Thank you.
Laura, thank you so much. It seems that your company provides a solution for everything we have been talking about. Yeah, almost. Very nice. I think I hand over now to David, which we got into.
Yes. So we will have now 25 minutes of Q&A. And I actually have a question that I didn't write down. It's a question that I wanted to ask in many panel discussions, and then I always dropped it. But today I'm going to ask. Because I think you are all three of you the right people to answer. So I always had these questions in mind. If when we go back in the past, and still now we go back to designers and architects, and we say, we can do everything you want, colors, shape, form, light, heavy. And this, of course, the message was well received, and then came back, drove up the cost. Have we somehow contributed to kill BIPV by doing that? I know it's provocative, but I would like to actually come back with an answer and tell me that I'm wrong. Who wants to start? If I can elaborate. Were we ready to deliver what we promised? Through the presentation for Laura, I would say that we are there now. But when we promised that, were we ready to do that?
So BIPV is a very complex industry. So we are talking here about industry. Is a combination of two different words that are speaking different languages, and that's make the things very difficult from industrial point of view. Answer to your question, we now have a good news, which is, you're right, BIPV is there since 30, 40 years. We have seen some first example in the late 80s, so very good example of BIPV. But the good news now is there is a clear and well-defined demand. So the market is there, and the demand is the only one driver for industry, the real driver for industry. So if the market is there, industry will follow. So, and the market will pull the innovation in the industry. So even if we have the solution, but we don't have the market, no chance for the industry to invest and to further provide solution. So now the good news is the market is there. But if I have to look at the reverse side, so the bad news is maybe the European industry is not mature enough. So there are solutions. We have seen EcoProject is on top line of providing technologies. We have some great example of industry that are already on the market. So 3S is, we have here one great example, but there are only few examples. If may I just few other 30 seconds, I was reading a very interesting paper from Solar Power Europe or IPV. They are mentioning how many companies we have now in Europe manufacturing BIPV. They are counting about 50 companies. 80% of them are startups or very small scale startups coming out from university research institutes. So very high skilled, but small scale. Few of them are very good exceptions. We have seen some names here. 3S is one of them, Onyx, and we have many others, but very few of them. And most of them are coming out from the PV industry. So most of them are PV companies that are trying to change the way they are offering the market because there is, they need to find some more added value market. So it's a very complex thing. So we have some good news, some bad news. Some other good news are coming from legislation. So we've seen some incentives.
We will come back to that later on legislation.
Okay. So
yeah.
I'm sorry.
No, it's okay.
I went too long, but
Laura?
Okay. So that's my feeling.
Yes, I think the provocation is right. So the cost is a big part of the BIPV, and it's a big part for every project in general. The key point here, and that's why how we try to answer this point, is not to customize what doesn't need to be customized. So actually in production, if you have to make a tile 600 by 600 millimeter or 800 by 800, the first point would be, okay, I customize the machine, I do the smaller machine specifically for the product. That's not the answer. This will just charge a lot the producer with customization cost, with a unique equipment made only for them, with the risk of a, I would say, prototype. So what we try to do is to standardize the customized, I don't know how to say, but, and that's, I think, the same aim of 3S. This is the only way to have a mass production of BIPV. So, for example, I take the tile example, the US tile example, where they have 1.2 gigawatt of tiles. It's clear the product is standard. But what we did was to have the standard machine for standard PV panels, so residential, industrial, and just work on an adaptation for a multiple tile loading, for a multiple tile management, or some molds, or some tool changes, so that the value of the equipment will still be there and remain able to produce also standard photovoltaic in case the market of BIPV is slowing down from project to project. Because we know BIPV has an issue. It's really project related. It's really building related. If the building delays, the project delays. So in terms of building, at least.
Thanks for this question. Thanks for the previous speakers. I come from innovation, research, and sometimes you need to have a vision. That's one important thing. And I think you very fast know what is possible. Maybe you're not ready to produce it automized, but maybe you're ready to produce it manually. So I think since a long time, it's possible to do customization manually, like special types and so on. With colors, it's a different topic. But as we heard, it's really the goal to standardize this customized modules. And I think 3S saw that issue very early, and we really tried to standardize this BIPV solution. That's why we have 4 standard sizes. With those, we try to cover full roofs and facades as much as possible. So with 4 standard sizes, and then we provide additional special sized modules or even inactive or like just plates which look very similar to really met that already. And we do that since a long time already. And somehow we have reached with that a high optimization. So back then we needed only to produce 4 standardized modules automized, and we could most installations we could do that with them, and then some special we needed to do manually. And this is changing, as we heard.
Well, thank you for the answer. I think you gave a convincing answer, so thank you very much for that. Luigi already almost spoiled the rest of the panel discussion, which is on, you already mentioned that a lot is happening, but maybe not enough in the EU. So let's go to that side now. So we cannot call them emerging legislations anymore because we've been talking about, by the way, if I say NZIA, can you raise your hands that you know what we are talking about? 25% of the room, 30%, so maybe, oh, you do, of course. Yeah. So we need to talk about them. I will give you the chance to explain what it is. So in terms of legislation and emerging legislation, what is the EU doing in helping also this specific sector in let's say, boosting manufacturing? I don't know who wants to start with an answer. Maybe let's do the other way around. Let's start with Rios from 3S, and then Laura, and then Luigi.
Thank you. As you heard, I invited to really work together on that we strengthen the backbone of the European industry, and that we have a certain autonomy. And unfortunately, Switzerland is not part of Europe, or maybe it's also good, I don't know. I don't give an opinion here. But what is clear, so we are not part of this Zero Act, Industry Act, Net Zero Act, but of course we are in the same environment. I mean, we are part of Europe, and our customers are Europe, many suppliers are from Europe. So we benefit from that, and we think it's a good direction to really have this, to protect somehow the European industry, and also, yeah, as you heard in my presentation, I talked a lot about that, that the conditions must be right. Yeah, that's okay.
Yes, so talking about the NZIA, or NZIA, how we say in Italian sometimes. This regulation, for who didn't hear about that, was a regulation discussed since practically 5 years at the EU level, at the EU Commission level, and it was approved finally in 2024 with implementation acts by mid-May 2025. The NZIA actually is a regulation which aims to shorten authorization processes, which aims to support projects based on sustainability and resilience criteria. And it is setting, I go more in what we need, at least for the building and the BIPV, it is setting some rules for a 40%, for a 30% NZIA content, sustainability, and of course, resilience content in the public auctions, in the building auction. All public building must comply with the auctions related to the NZIA criteria. So this aim to shorten regulation process at one side, but on the other side, it aims to boost and restart the European, let's say, industry. That was what was the aim of the Commission. Now we have time until 30th of December, I think. Every member state need to take an action and must take an action to rectify, or basically have in their own regulations the NZIA criteria. Italy was one of the forefront on that. We know very well that they started to have the FERX standards, the FERX maybe for standard PV. But I think for the IPV industry, for the BIPV industry here in Italy, we will see really big boost given by the NZIA, because many public buildings are old, many buildings need to be refurbished, and for every auction, for every new building, for every refurbishment, they need to comply. So it's a must. And the regulation is stating it very clearly. So it's shorten the time, but also gives more criteria of CO2 emissions and sustainability, clear supply chain. So it should, let's say, cut off non-sustainable, or let's say Chinese mostly, competitors and also producers, benefiting the Europeans. But it's not written anywhere that is supporting Europeans. So just to be very clear.
Yeah, we might come back to that later if there is the chance, Luigi.
I have not so much to add, so she's the expert. But so NZIA, for my perspective, is the second good news. So one good news is the market demand, and the second is legislation is moving. So it's a very good tool that we finally see as a pool for the industry. If I have to look at some problems with this legislation, one of them is, for my perspective, is still too generic. And this is the way Europe is generally working. It comprises a lot of things, as Laura said. But there are not yet, I would say, maybe the different countries when they will adopt in legislation, the guidelines, they will be more specific. But what I see is too generic. We should, as Europe, we should take the risk to focus on some specific application. This is a way to not spread too much the money and where to invest, and to focus on specific industry, because industry needs specific trajectory. We are spending as Europe a lot of money on technologies, for instance, that will never be made in Europe. A lot of money are now for instance, high efficiency cells. But there are no one real cell industry. So there are some projects, but there is no real gigawatt industry of cells in Europe. But we send a lot of money on perovskite, new technologies, and new technologies of cells. This means we are spreading the money, and we need a clear trajectory. So I hope that once this European level guidelines will be translated at country level, there will be a more specific trajectory that will pull the industry.
Last question from my side before I give it to Heinz. So I think it's really related to what you just said. So what we see in utility scale PV modules is that if there are companies trying to reshore manufacturing in the EU, the first question from the investors is, do you have off-takers? Do you have buyers of your PV modules? And the answer is no, because you are not cost competitive. A part of the NZIA tenders where you are the only one potentially who could compete if we introduce Made in EU. But for the IPV market, so Luigi, you mentioned now we have market. So do you think it's slightly different? So if someone in Europe, like 3S and all these startups, they want to scale up, will they have an easier life and convince investors because there is a market for the modules, or the same cost pressure comes from competitors from outside of Europe, also for IPV product?
No. But my feeling is at this stage, cost is not the main issues, and this is exactly the reason why some European industry, PV industry, are targeting this specific market, because there is some added value that can, so it's a completely different market. But from another perspective, this is of course one of the limitations, because you need to scale up at high level, as Laura said, without scaling, and to make a BIPV products a standard, we need to go massive with that. So those we stay on customized. Most of the sales in BIPV are project-based. So this is limiting the scaling and massive introduction of IPV. The problem is, from my perspective, it's a combination of two words. They are not fully aligned. Construction, building, industry is not mature enough to include, in most of the cases, energy generation into their products. And the PV world is not standardized, massive, and scaled enough to fulfill the requirements. So we have some exceptions, but the two worlds are still not aligned.
If someone else wants to answer this question before we move to
Yeah, so I think you say that there is the market. Yes, I feel that there is the market as well, but on the other side, we see also some of our customers struggling by the fact that the regulations are not protecting them totally. So we know very well to have a building construction, a building integrated PV, we need to comply, the producer of the modules need to comply to 10,000 complex and really fragmented local regulations, province regulations, building regulation, which change from, I would say, I don't know, 50 kilometer from 50 kilometer, even less probably. And so this type of compliance, it's costly, it's expensive. And this is our market, it's a local market. It should be done by Italians, should be done by, I would say, Swiss or European in general, capable of complying and to provide a product which is quality-based, but also respecting all the regulations and the requirements. And here what we are noticing is that the producers start to have competition from Asia, also in BIPV. And because they seem, I mean, of course they have also access, easy access probably to these certificates, or God knows whether all the certificates are really complied, but still we see competitions from Asia. I think BIPV has to be a local market, has to be a European market. Every country, every roof and knowledge on the roof is country-based, province-based. And so seeing, let's say, from far away that we have from the Far East Asia products competing, it's painful. And for the producer, for the BIPV producer, doesn't allow them to scale up because they have to comply with really ridiculous prices sometimes for a very customized product. This is, I would say, an additional challenge. So the regulation, to me, should prioritize not only sustainability criteria, not only resilience criteria, which somebody else may comply, but also made in EU. And that's the key.
And I think one topic I raised already, so thanks a lot, I really agree what you say. Yeah? And it's not a free market. We have high subsidies in some countries, which we don't have in Europe. It's not free. It's also not the realistic prices we have from China, I would say. So it's like, if either we make some taxes or whatever, that we have a fair situation. Of course, it's not the same, this is clear. But I think we see that also in other industry, like the car industry or other. I think, as you said, we invest a lot in research and development. We maybe then innovate and make proof of concept. And then when it's time for scaling, then all is gone. And I think this is maybe a big topic to change that. And if we make right regulations or framework, what I said, then we can have industry here and have also independency, and I think it's very important in the current situation. Yeah, and also to reach the energy transition is also a big topic. Yeah, we want to reach that, and we don't want to be dependent on, I don't know, a certain market or a certain. We want to do that also by ourselves and strengthen ourselves, I think. And I think another thing is the government or the public should be like a role model. Like, they should say, okay, all governmental building, they do BIPV. This is clear, it's a must. They are like a role model and say, these buildings, it's for sure. So that the market is enlarged automatically. Maybe not for private or maybe, I don't know, but like a plan, to have a plan.
Okay, thank you very much. I want to go a little bit back to the beginning when Luigi said the market is there and it's developing. And my question is always coming in principle from a regulatory part. Is it more the appeal to the customer where you see the market, or is it more of enabling regulations, guidelines, standards? Or what would be the major impact for the future growth? Because I think on the appeal side, you're all very innovative and working very strong on it. And it's always surprising to see, even here on the exhibition, what products are coming out.
Yeah, no, the driver for this market demand is, as I said in my presentation, we started from macro trends. There are some trends that are worldwide recognized, that are now clear and visible. Electrification is one of them. The energy demand and the way we have to generate electricity will be different, and there are already some demand for changing the way we are currently generating, not only generating but managing electricity, storage, software for controlling, managing the electricity in different environments. So we have to increase a lot the quantity of electricity that we will generate, and we have to change the way we will generate. So distributing energy, electrification everywhere, this is clear now, and there is a demand. Regarding standards, so it's different. Standards are one thing, legislation are another things, but standards are following. They're not ready yet. So the standards are not the driver, can be a limit now.
Mm-hmm. Okay, let me just formulate a little bit more precise. The problem BIPV has is actually going for regulation of buildings. So we saw, for example, the presentation on fire resistance and so on. Now, if you would ideally have one single building standard in Europe, which we never have, because we have, I think, 1,200 sub-chapters or something like that. Yeah. If it would be unique, then Asia would be the first to comply with them, most probably.
Oh.
So is this diversity not a certain advantage for also production facilities?
I will comment even what Laura said about competition. Competition is not the devil, okay? Sometimes in industry, competition is good. Fair competition is good. Fair competition is good. But we are talking about cost and prices. Mm-hmm. So what my expectations are, competition should pull and drive European company to diversify. By what? By quality, as you said, by innovation, by proximity, by developing solutions, not only products. Those are the key for the European industry to compete, even without specific incentive of legislation. So quality, proximity, and integrated solution.
Sorry, we have to. So we have. Will be a fighting panel.
Yeah.
So good, I agree, Luigi. Thank you. But according to me, it's not sufficient. So the fair competition, unfortunately, is not always there. We are seeing in the market a huge overcapacity and a huge, I would say, direction. Asia, it's, of course, pushing for export. It is having a lot of support for export. The president said it very clearly. They want to become the hub, the industrial hub of the world. So they want to export and feed us with all kinds of products. And that's what they're doing, cars, devices, and everything. So it's clear, this is, it's a strategy forward. What is the strategy for you? That's the question. What will be our strategy? Just simply innovate? Because the innovation, I totally agree. You saw the quantity of companies, which I just presented, doing unique products, diversifying, already doing this with funds and not with funds as well, also with private funds. So we have huge examples and beautiful examples of really innovators, really researchers and inventors, I would say, of gorgeous products. They cannot succeed if they don't have a framework that supports them, because they will simply be eaten by the competition, unfair competition. We do not share the same values here in Europe with Asia. That's a fact. We don't work 120 hours per week unpaid. We don't work if we are pregnant. We don't work if we are a child. We don't work, so not always we have the fair competition with Asia, unfortunately. We have to comply with a lot of European, of course, CO2 emission standards, which not always they do have. So there is indeed a difference. We cannot deny it. I mean, it's getting better. It's, of course, harmonizing worldwide. But there is a difference. The European product reflects European values of life and of life standards, sorry to say. So we are not competitive with a Chinese equipment manufacturer. We cannot compete because we do not share the same base conditions to compete. So that's why I think we should give, the regulation should give a premium to a European product. If we have a building constructor that has to choose between an Asian product or a non-European product and a European product, it's clear we need to fill the gap of the difference between these two products with maybe credit, tax credits, incentives, some kind of support. Because if the European product costs 40% more than an Asian product, but I have a tax credit, then the European will buy European. So if there is some kind of protection, which doesn't mean not complying with the WTO. So you can choose everything, but you will have a premium if you buy European. This is the type of regulation which we need. Sorry to be, I know that...
So you mean tariffs, import tariffs?
No, I mean criteria, preference EU criteria. Mm-hmm. As clearly Raya said, we need to have some kind of formula to have all public building, for example. If we are using our own public money, our EU money, this should be done with EU products to generate a real macroeconomic effect.
Including publicly rented buildings? Because that happened with the Building Energy Efficiency Directive for public buildings.
We can explore.
Okay.
You know, my position is a bit integralist on that. But
I think the audience is also eager to make some questions before I come at the end also to you. Are there any input or questions from the audience? Yeah? We have seen there one. Here's one.
Hello, Jean Rodier, Wattway. I have a simple question on BIPV. You're competing with also electricity production from standard network. And I think you don't have to forget it. So how do you manage this competition? I'm a bit...
Thanks for the question. We don't see us only as electrical, as our products don't only do electricity. It's part of this building skin, so it has a function of a building skin. It protects this building, but has also aesthetical aspects, and with that, it's not only. So you cannot only compare electrical costs to each other. I think that's it already, the answer. Very good. And maybe to answer what you said regarding market, we have 20 years market or 25 years market developed, and it steadily grew. And Switzerland, the government has supported that. And what we have heard today, Switzerland has like some guidelines how fire safety and so on should be done. And of course, still we have some differences in between certain areas of Switzerland, but it's possible, and it is a proof of it's there, yeah.
Hello, I'm John Morello from Frieslands. I was in the conference last year, and a very good conference this year. To Lara, we've been manufacturing our solar tiles in China for 8 years, nearly 1 million tiles. It's not true that the Chinese work 120 hours a week. There's so much automation coming into BIPV manufacturing. And so, in fact, you walk into any module line in China, there's very few hands touching. What China has done is automated at a faster rate than Europe and the USA. And when you go to see what's happening in China, you realize China has something that the rest of the world doesn't have. And it's supply chain. There's a phenomenal supply chain emerging in China that I can't see in Europe or America or anywhere else. And I was just in Shanghai 2 weeks ago, and there's 10 million cars, 51% now electric. And the quality of the cars, the technology in the cars, I don't see anything like this in Europe. And they're coming quickly. And it's the supply chain and the automation. It's not they're working 120 hours a week.
So thank you for the question. I never say that China is not automated. So I'm just saying that we don't share the same values. So not always, let's say, they reflect the European values. So you're totally right. China has a gorgeous supply chain, an amazing supply chain. Every 6 months that we go there, we see innovations, buildings, electric vehicles, electric mopeds, electric everything. So they really set the path forward to develop the supply chain. They also set some little details in their regulations. For example, for every factory, they need to have Chinese equipment. They cannot source equipment outside. So these allow the whole industry to keep on developing. They cannot use foreign raw materials. They must have Chinese raw materials. And so the Chinese raw material producers start their factories, have a long-term regulation base where to make investments. So they have a real long-term, gorgeous, in my perspective, vision over the supply chain for photovoltaic and for energy, because for them it's strategic energy. The question is whether it is strategic also for Europe, because we can become installers, service providers, also US. US is already a country doing services, renting everything and having, actually 20% of US is only manufacturing, only 20%. They don't even make the bread for themselves. So the point is, do we want to reach that point and also be losing back our industries? That's the question. We can lose them, but it needs to be a conscious choice of what we are doing. Or we can still try to save them and to support them, at least the existing ones, and to give a long-term regulation framework so that they can reshore, restart, or at least survive, I would say. Public building is a solution. I'm just giving some ideas, throwing ideas, but there is nobody from EU. So public building made with EU products, at least public building. That's the idea.
Can I add something here very short?
Shortly, yep.
Okay, so what we heard is China is really not, it's a protected market. And they have some also other subsidies, hidden subsidies. As example, certain companies, they get like a fixed energy price at a very low level, or that's not everywhere the case, but maybe for certain regions, or they have like rent, like for a certain time they don't pay rent, or they get even the land for a certain time, similar in China, or they get a special funding, and so it's really protected, so it's not comparable what we have here. It's really challenging. So I heard your question. Of course, we had some support with research projects. This is of course we had, but I think it's not comparable. It's really not.
Okay, ladies and gentlemen, first of all, before I'm thanking our podium members here for the nice presentations, I would like to ask each of you one single sentence, what you will say in a year from now here at the next IPV. One sentence only you want to be quoted with for the future of BIPV products. So we start there. One sentence only, where do you want to be a year from now? And what do you need for it? Yeah?
I think we are in the right direction. So I think Honestly, I don't know. I have a hope, but
Okay.
okay, I will disclose in private, but I have my idea.
Okay. Yeah. Okay, Laura.
Maybe I'm less politically correct, so I will say the sentence. We hope to have more surface solarized with EU-made products. That's what I hope.
Okay.
As the IPV conference is Italy, we will have much more implemented projects in Italy. Nice 3S solutions.
Okay. So what I would have expected also is we will double our exports into China. Thank you very much. I think it was a very exciting discussion, so exciting that we all need now a coffee, where we also probably can continue some of the debates. Thank you very much for attendance, and thank you again for the podium. Thank you.
We wait for you for the coffee break. We run with 15 minutes delay, but don't worry, we will recover with the lunch break. See you outside.
So welcome back after the coffee break. I hope you still have some energies to continue with the discussion. It was a very engaging discussion, what we had in the previous panel. So we hope to keep the same interest also in this panel. So this session is titled PV Technology, Castle Building Facade Elements. I'm Laura Maturi, I'm IPV team leader in Eurax Research from Bolzano, Italy, and I'm honored to chair this session together with my co-chair, Rémi de Bétigny from CEA in France. And I'd like to thank our 6 speakers who are with us today. Unfortunately, one speaker is sick, who is Tarvo Kargenberg from Parking Lot. So we will, hear your presentations regarding both research studies, but also practical applications related to different ways of integrated PV into the built environment. We will see examples of facade integration, integration in noise barriers, up to active energy environment cities. We will also look both at materials development with developments, for example, in lead-free solutions and perovskites, but we will also see fabrication of customized PV modules and IPV manufacturing lines. So, before we start, I kindly ask all the speakers to keep their presentation within 10 minutes. We have a quite tight agenda, so thank you already for that. And I'll hand over to Rémi to introduce the first presentation. Thank you.
Thanks, Laura. The first speaker is Ringo Kopke from CSP, Fraunhofer CSP. He will talk about the reliability of lead-free interconnected BIPV metal facade using PERC on heterojunction technology.
Yeah, thank you. Thanks for that kind introduction. And I would say thank you for the chance to speaking here. My name is Ringo. I'm working at the Fraunhofer Center for Silicon Photovoltaics. And I subdivided my talk into 5 parts. At the beginning, I want to give you some information about my institution. Then I like to motivate the topic building integrated PV. I guess all of you are still motivated, but maybe I can give you some more references that you can share to other people. Then I will describe our experimental design. And finally, I like to share my results and summarize my talk. Well, the Fraunhofer Center for Silicon Photovoltaic was founded in 2007. That was, I would say, the time when the PV production rises in Germany. We are installed to support the local PV manufacturer located, let's say, almost in the middle of Germany. And we have today a budget of around 800 million per year. And currently 100 employees are working at our facility. We do research along the entire value chain, starting with the crystallization and ends up with the recycling, plus the analysis of hydrogen technology. It's a small part of our institution. And I am working at the group of PV modules, components, and manufacturing. In a few words, we are manufacturing solar module prototypes, test them, and looking for defects, and try to improve the modules. Well, regarding the PV integrated modules, I like to share. Well, the animation doesn't work. We see everything right now. But yeah, on the right-hand side, you see an image of a study for the buildings of Munich. They look for the radiation of each phase of the building. And I like to say, please keep an eye on the green-looking areas, because that are the facade areas, not the red one that are the rooftops, and not the blue one that are shaded areas. And the study says that there are amazing big potential for producing energy with the facades. Residential and industrial building types are usable, and especially the medium height buildings are most common, and they calculate that there are more than 6 gigawatt hours per month are achievable. To underline the motivation for the building integrated PV, I'd like to show you here a figure of a test setup we built on the rooftop of the at the top of the Fraunhofer CSP. You see the energy yield, or let's say the power generation for one day for the 4 seasons of a year: fall, winter, spring, and summer. And at this point, I want to underline that, especially in spring and summer, if you are using a south, east, and west facade, you have a quite homogeneous energy production. If you summarize all the energy over 1 year and compare it to a standard solar power plant where your solar panels has an optimal orientation to the south in the right angle, we can see that we are able to achieve with the south orientated facade almost 70% in comparison to a PV power plant. And there's also more than 50% for the east and west orientated facade. And if you are building you only have the possibility to install PV at the north side, there's also a chance to achieve up to 27% in comparison to a PV power plant. The question now is, if you want to install building integrated PV, what's about reliability? We heard something about this today. And in my case, we wanted to manufacture an aluminum facade building integrated PV. And there we have to counter a very huge thermal expansion that's caused by the aluminum. And therefore, we make a design of experiment to find the best material combination. And we changed the cell connection type. We variate the cell types, the encapsulant material, and the electrical insulation. Here I show you the table of all the batches of mini solar facade modules we're manufacturing. You can see an image on the right bottom side. We start with the reference batch. We use standard material, a standard soldering connection of the cell. The only different material was the backside. That was not a backsheet or a glass. There we use the aluminum facade. We changed the connection type. We also used electrically conductive adhesives, 2 different types, an epoxy-based adhesive and an acrylic-based adhesive for the cell connectors. We used different solar cell types. We used the PERC cells, and one batch, number 8, was a heterojunction batch. We changed the encapsulant. We use polyolefin encapsulant and the older standard EVA encapsulant. And we changed the electrically insulation layer. Maybe you can imagine if we put a solar cell string onto an aluminum facade, we need something that is not melting during the lamination process to keep a distance between the electrically part and the aluminum backsheet or facade element. Therefore, we used a modified polyester foil, standard backsheet, and a polyfiber mesh. After that, after the manufacturing, we put them all together, or not together, but step by step, into a climate chamber. On the right-hand side, you see a figure of the biggest climate chamber we have in our facility, and we applied a damp heat test and thermal test according to the IEC. Now let's go into the results. On the in the table, you see the batches that run through the damp heat test. And on the right graph, you see the relative power loss of each module. Well, at the beginning, I can say that all modules passes the IEC criteria, but I guess all of you know that it's quite simple, less than 5% power loss after 1,000 hours. We increased the testing time. The best we have seen was the soldering batch and the reference batch for the ECA1. We could see that aluminum facades demonstrate a better moisture barrier in comparison to a standard polymer backsheet. We can see that the heterojunction cells perform quite moderate. They show a degradation, but still in an acceptable range. And we see also a high degradation for the second backsheet module. This backsheet module we mounted onto the aluminum facade with an adhesive only. And there we have also moisture infiltration. If we have a look at the electroluminescence images of some samples for the winner batch, the soldering batch, we can see there that we started with a quite poor quality of our solar cell string, but we could see that the defects are not rising over the 3,000 hours in damp heat testing. In comparison to that, we see that we have a high moisture infiltration for the batch 2 and the batch 3, the most for the batch 2. And we can see that we have a less degradation is visible in the electroluminescence image for the heterojunction batch. If we now have a look at the thermal cycling test results, it looks a bit confusing. So the first general message is that almost all module passes the TC200 test, apart from the batch number 7. That was a polymer mesh as a separator between the string and the aluminum facade. Apart from batch 7 and 5, we can also say that all the material combination passes the TC600 test. We can see that the backsheet module performs slightly better. That fits to our assumptions because the backsheet module has not so high thermal expansions like the aluminum facade. And I have to apologize because the tests are still running and not finished yet. I try to pick up one example. The batch number 6, we see here an inhomogeneous image of measured by electroluminescence, and we also use the magnetic field imaging that allows us to see the magnetic field that is generated by the current that is running through the solar cell string, and we can it indicates to areas with a high or low current flow. Especially the high current flow is here an issue. And if, especially on the right-hand side, you see a very dark red area, and this is correlated to a bad cross connection, to a bad cross-connector connection. And it ends up, if only there's one cell connector that has to take all the current with a failure image you can see on the left-hand side. For the batch 6 after 600 cycles of thermal cycling. We saw an equal image also for the batch number 5 when the current is too high for a single cell connector. Yeah, with this, I like to sum up my talk. Hopefully I can give you the evidence that aluminum facades are mostly ready for use in building integrated PV. maybe apart from the weaknesses of the cross connector we have to fix. On the right image, you see a prototype of an aluminum facade module we manufactured at our facility and presented this year at the Intersolar in Munich. We have seen that the aluminum facade has less moisture penetration in comparison to backsheet modules. And we can say that there is no differences between the cell technology and reliability. We see an equal behavior that is independent from all the material variation we have done in this experiment. Yeah, and finally we saw weaknesses at the cross connection. We still have to improve. With this, I'd like to thank you for your attention. I like also to say thank you to the German government for founding this project. And yeah, thank you for your, and thank you.
Thanks for the presentation, Ringo. I've got a very little question about the cells technology. Are you planning to use maybe TOPCon technology for its efficiency? And what could be the challenge using it?
Yes, we plan to do this. Maybe one remark: the TOPCon cells are missing because there were investigations for a project where we are the only partner who was manufacturing the strings and the cells, and because of our facility, we are only able to handle with heterojunction and PERC cells. It's related to the size of the cells, and this is what our stringer can do. But yes, we applied for a second project regarding the aluminum. Hopefully, we can start in next summer. There, we want to use all current cell technologies. Yeah.
So thank you once again, Ringo. And we welcome Yu Yao from Sunwell Power in China, who will share with us insights on development and fabrication of customized solar modules. So Yu, the floor is yours.
Thank you, Chairman, for the kind introduction. I'm Yu Yao from China, from Sunwell. It's my pleasure to be here to share with you our experience while we have different requirements from customers and our experience of making customized modules. Yeah, so a brief introduction of our company. We actually have two divisions. So here I'm just going to introduce you our module fabrication division. We have more than 2,000 square meters of fabrication fabrication site. We have 8 years of making solar tiles. The capacity would be more than 300,000 tiles a year. Actually, from customized requirements, we have less than 6 weeks delivery lead time from design and discussion of the requirements to a delivery of the first batch of prototype samples. And we are located in Suzhou. It's quite close to Pudong Airport, and Jiangyin is our module factory. It's by the Yangtze River. So if we look at the bill of materials in a module, which are the components we can customize, basically we can talk about everything that can be customized. So in our experience, we have done modules with different size, different color, and we have also used our special electroplating technology to develop like a souvenir when we moved our factory. So the picture on the top right, this is with our company's logo. We made it by patenting and electroplating technology. So this could also be done when the cell is still functioning. You can make it in a module. So when we look at the glass, if we want to customize, I took a picture from a typical glass production line. So the feature of a glass that needs to be customized in the production line of a standard glass is typically either it's floating or the white solar glass, and the thickness. So if we change the thickness, then there's the tool roller that is used to squeegee a liquid glass, the molten glass, into a solid form has to be tuned. So what are the challenges there? The capacity of a solar glass, it's in a unit of 10K tons per year. And by end of last year, there are running, so in operation, 102 furnaces, altogether 457 lines. So average one furnace has 3 to 6 lines. Each line can be producing one type of glass. So for example, for the BIPV application where we got requests to use 4mm glass, it means that one line, that's the minimum production of one glass line, it can supply 20K square meter of 4mm glass. So it's quite a big volume when in the last session, we were talking about if customized module is killing it or it's helping. In this sense, I think the point or one of the reasons I'm here is to say that we embrace the customization of modules because we want to cover different surfaces as much as we can. And therefore, we need customized modules. However, we need also kind of work towards a standardization to help in the supply chain to get the things that we all want in the product. And there are also other aspects in customizing the glass. These are after the normal production, for example, the tempering and putting anti-reflection coating or printing them with different colors or cut into different size, drill the holes in different locations. These all needs work in the supply chain, and this is not typically done in the original glass sheet factory. And if we look at encapsulant, actually the market share in terms of the types of encapsulant, we see it's dominated by EVA, POE, and also the EPE. In the others range, which is less than 1%, my understanding, this would be mostly PVB and also TPO for some thin film application. The conventional or the mainstream encapsulant itself is also evolving over the years because they need to solve the problems or issues when the cell technologies are developing. For example, the EVA, they are training, so the development would be to have a formulation that's anti-PID and to have a low acid, especially with like TOPCon and heterojunction cells. And therefore the EVA is basically in the 2010s, it's developed to polyolefin and the TPO. And there so when people work enough in the lamination process, they know there is a smaller process window, lamination window for POE. Therefore, there is this combination of a sandwich layer, EVA on the outside and the POE in the inside to combine the good reliability of POE with the good processability of EVA. And its function to provide aesthetics, for example, from the color, is also gaining interest. And our approach to have a colored module, for example, on this project, that's a fabulous building done by Façade, our partner in Switzerland. We have the solution, actually we tested different colored thin foils, and we use it in combination with standard encapsulant. And the logic there is we want the colored thin film to provide color options, and we want a standard encapsulant to provide the normal module processability and reliability. And here we also have, so if we put that into volume production, we would also have a MOQ issue if we just go to any encapsulant supplier, because a typical extrusion line, they are 200 kilo of encapsulant needed per hour. So we have a small lab extruder, and that is consuming 50 there's throughput, 50 kg per hour. Imagine we produce a film that's 100 microns thick. It's already 150 microns per hour. So it's, even if it's a lab scale extruder, it's also quite big in volume, but that's how we handle the small but very customized requirement. And with our colored module, we have typically power loss compared to a standard BOM, 8 to 15% power loss. And for solar cells, we know in the industry it's evolving, or the wafer format is changing, the cell technology is changing. So we can customize the solar cells. One route is after cell production, the other route is in the cell production. So afterwards, typically we can cut them into different sizes and make the string. Or the route B for back contact, what's typical today is you can purchase the back contact cell, but it's without the isolation resin and it's without the solder paste. So these are the after process that is now an intermediate step between cell and module production. And in cell production, we can either customize the screen print or we can customize with electroplated patterns. The complexity of managing different customization is also marked with different numbers of stars. So here, for example, is a copper-plated cell with the shingle. And the same technology we used to make this souvenir. For example, in our that's our the Sunwell's main business. When we started, we were developing the turnkey line for copper electroplating on heterojunction solar cells. So we took an ITO precursor, put resist on both sides, make the patterning with like a lithography process. So we developed all the tools for them and also the materials, and finish with the metallization. That's our main work when we were first a startup company to a company we are today. We spent 4 or 5 years developing this. And so we have a 1 gigawatt pilot line. It's a pilot line on a customer side. And this line, we have some access to make customized solar cells. And what else in a customization? Typically, junction box, there are already a lot of models exist. So we don't ask for ODM unless we really have to, because there's a MOQ issue. And for frames, we also make some special design, for example, to install the tile shingles. So these are the different junction box. And in our test and certification, I want to highlight that we have also the possibility to measure AM0, and also like a standard module fab, we can make a glass transmission test, IV and EL. We also developed our in-house PL system for tandem cell structure. So with one click, we can measure the top cell and the bottom cell to identify the defects. This would be our product development process. We take demand or product spec into discussion and finalize the first prototype design, make the process optimization. It's typically 4 to 6 weeks time. And then we often give a feedback of how the first batch was done, how the results are, what are the lessons we learned, what we need to go into the second loop of optimization. And then that brings me to the conclusion. So the industry's standard bill of materials is mostly optimized to balance power, reliability, and cost. But here, the community here, when we discuss about IPV, there are a lot of materials we discussed yesterday and today that needs to be customized, and they often come with different challenges. And I think it needs quite a bit of a collective work that we can optimize it, and that's the key to the success for everyone here. And thank you for listening.
So thank you, Yu Yao, for the very interesting presentation. So I would have several questions, but I would ask only one general, connected to the previous discussion we have in the panel before, related to European and China policies. So we have now the opportunity to have a voice from China with us. So I would like to hear from you some insights on the situation in China related to BIPV, so challenges and opportunities, and also in which way policies are supporting BIPV manufacturing in China.
So we are also active in the Chinese BIPV community, in the sense, for example, most of our products we are making in the line today are solar tiles. In China, there is an industry standard that's in the draft phase to define the standard dimension of a solar tile. That's also working because every BIPV manufacturer, they have encountered the same issue, much the same as I talked about before, different size, different formats. So the industry is trying to define a range of dimensions, a range of glass, some sort of glass thickness, and also the testing standards so that it can help to bring BIPV into, for example, mostly in the buildings, can move quite quickly in that direction. And but in general, I think the architects in China, they have less exposure to PV than what I feel in Europe here. But the government is putting policy like for new buildings and for renovation, there's also a certain percentage that needs to be covered with PV, but not necessarily BIPV. So in general, I think as the technology develops, as the material develops, there will be a bigger market for IPV in general, and that's why I think also from the population, the audience that's coming into this conference this year compared to last year, there's also this trend. There's more interest, there's more development work, and still we need to work harder, I think.
Thank you. Thank you again. Let's move to the next presentation by Lison Marté from CSCM in Switzerland. The title is Prelaminates, Enhancing Flexibility in IPV Manufacturing Lines. The floor is yours.
Thank you very much for the introduction. So, yes, I'm Lison from CSCM, as Alessandro presented a bit earlier today. And the topic here is the prelamination. And as well described before by Yu Yao, integrated PV really need a high degree of customization sometimes with variable module sizes and variable string size. Our approach here to tackle this challenge is the prelaminates that we define as an intermediate assembly of strings and encapsulant designed for storage prior to final PV module lamination. So the advantage of such prelaminates is first the flexibility that you can bring in your manufacturing line. For example, as a buffer process, if you need different string sizes, you can produce one length and then prelaminate it, store it, and then produce the other lengths that you need for special products. There are also other advantages, is that we can store the strings in the air like this. In the prelaminates provide the mechanical and environmental protection from the moisture and the oxygens, for example, so we do not need to store the strings in special conditions. It's very easy also to manipulate those prelaminates, and that can be helpful for maybe curved modules or such. Our process is this one. So we have a string of any length and we put what we call the interlayer and we prelaminate and we have this prelaminate. So basically the interlayer is a polymeric transparent sheet. Then we can store it for a certain time and we can make a final module. So we add the encapsulant here, EVA in our case, and glass, or it can also be glass backsheet. And we laminate it and have a final module. In some case that we haven't studied, we can use, we do not need an extra EVA layer, for example, we can just relaminate everything, but we haven't studied that yet. So this process raises many questions. First, what is the most adapted material as an interlayer? What is also the impact of the storage at the material level itself, so how the material properties evolved with the storage time, and what is the impact of this interlayer on the module performance as well as on its reliability. So for the question what is the most adapted material, we first request, of course, several properties, high transmittance. We also need the material to provide an environmental barrier and mechanical protection. And also it needs to be compatible with PV conventional processes and materials. So for that, we evaluated two materials. One that is a known commercial POE, of course, that is available and compatible with PV materials, of course. And on the other hand, at CSCM, we have developed our own material that we called IPO, so interlayer PO, that we formulated on purpose. We have our own extruder, so we can really develop polymeric material for PV. And one of the there are differences between the commercial POE and our IPO. First, our IPO is very rigid and non-sticky, so we can really easily handle the strings after prelamination. Whereas the conventional PO, after prelamination, we cannot really stack them on top of each other. They are very sticky. So this is one of our main improvements. And also, it's thinner than conventional commercial encapsulant. And in that case, in our first trial, our IPO contained UV blockers. So of course that lowers a bit the performance, but that can be improved by removing UV blockers. So after that, after developing our material, we wanted to test it and see how the storage impact its properties. So we made prelaminates only with the material without the cells of IPO and POE and stored it up to 6 months and checked its adhesion to the solar cells or EVA. And also we performed rheology, DSC, FTIR. And the first results showed that the adhesion on the solar cell for both IPO and POE are good, even with 6 months of storage. And same for the adhesion between the IPO, POE and the extra layer, so the EVA. Then for the rheology, we saw an increase in viscosity seen by the max tan delta of the IPO decreasing, and also for the POE. But what is important and what we see that the material can still be processed for the final lamination. So it's still okay, still good news. And for the DSC and FTIR, we haven't really seen any pronounced variation in that. So material properties changes a bit, especially the viscosity with increasing storage time, but the material can still be processed. And we'll see if there is any impact at the module level. So after material testing, of course, we tested the module. So again, here we made prelaminate strings with IPO and POE, stored it up to 3 months, and then checked their properties, electrical properties, and how the modules degrade under thermal cycling and damp heat. So for the initial performance of the module, as I said, the modules with IPO have UV blockers, so the initial performance is lower related to ISC losses. And we also observed slightly yellowing, but the EL of the final modules with the IPO are good. For the POE, we have higher performance compared to IPO because the POE was non-UV blocking, but we see some interconnection losses on the EL, as we can see here. But this is probably related to the fact that the module is not designed to go through 2 laminations. After that, we checked the reliability in thermal cycling. So we see that modules with the IPO after 600 cycles, so 3 times IC standard, they remain quite stable at good performance and perform similarly to the reference EVA modules that is not prelaminated, just a conventional EVA module. Whereas for the POE, we see initial losses also, and this is related to fill factor, and we see interconnection losses. Again, this is probably related to the fact that the POE go through 2 laminations, and this is not designed for that. But maybe if we adapt the processes, we could we could improve that, but this requires a lot of time and resources. For the dump heat testing, basically all the modules that either had IPO or POE, they pass to 2 times IC, so 2,000 hours in dump heat without degradation. So it's good results, except that modules are getting more yellow, and this is probably related to the presence of EVA. So on that, I want to conclude that these prelaminates have many advantages for the production, especially we can really easily handle the strings, and also, for high customization, it's very interesting. Our initial finding, especially with our own IPO, are very interesting. We have good reliability, especially in thermal cycling and dump heat. And in our next step, we really want to improve our formulation by removing the UV blockers and also test it with TopCon and perovskite. So we're currently testing the prelaminates with TopCon, and we observe good results. So on that, I want to thank you for your attention, and also thanks all the CSM team.
Thanks, Lison, for the great results. I've got one question that was mentioned in the conclusion, but is it possible to use a Seeker interlayer IPO just in one step process?
So we haven't tested it. We can make, and we have higher, thicker IPO. But I think here the issue is the adhesion of the IPO on the glass. We can improve it, but this is I think the bottleneck here.
Okay, and is it the same temperature for the two different processes, the first one and the final one?
No. For the IPO not, but for the both. No, for both. Sorry.
Yes. Thanks a lot. And we can applause, maybe.
So thanks again, Lison. And we welcome now our next speaker, Noah Tormena from the University of Padova. We will go now deeper into lower TRL level, and he will talk about stability and optical performance of semi-transparent perovskite mini modules for BIPV. Thank you, Noah. The floor is yours.
Thank you very much. Hello, everyone. So just to jump straight into my presentation, I'm going to start by introducing the devices that we have worked on. So these are formamidinium lead bromide perovskite solar modules, in this case, mini modules. So high band gap absorber, you can see a 7x7 cm mini module, roughly 19 square centimeters of active area, and there are 6 series connected cells obtained via P1, P2, P3 laser etching, and glass-on-glass encapsulation. So just as the basics, we can see that this stack allows for semi-transparency, which is the property that we will be focusing on for our BIPV considerations. But what does BIPV look like, or what could it look like for this kind of device? Well, here we can see the transmittance of these devices. So below 550 nanometers, there is very low transmittance in accordance to the absorption of the device, while above 550, we have a quite decent transmittance, up to 70%. And this allows to obtain, at the bottom right, you can see the orange spectrum, which is the AM 1.5G solar spectrum filtered by this kind of device. And it would look something like this image on the right, which doesn't really look so convincing, right? The indoor comfort would not be so ideal. So what can we do to compensate for this? Well, for example, we could use, in conjunction with these devices, basically a blue tinted glass. So here we see BG25 tinted glass by Schott, commercially available, and it has this transmittance spectrum, which is fairly complementary to the one of the perovskite devices, and it would result in this blue spectrum if it filtered the sunlight spectrum. And as you can see from this image on the right, this is more or less what it could look like. And you can notice that the indoor comfort can actually be improved in this way. So to continue along the line, we have found that the optimum is more or less 8:1 perovskite to BG25 surface ratio. So it's important to notice that we are not talking about overlaying the two materials, but to put them one next to the other. Otherwise, we wouldn't have sufficient light coming through, and this wouldn't work. So with this 8:1 surface ratio, we would achieve this yellow spectrum. And you might ask, but how can we define the 8:1 surface ratio as the optimum? Well, to answer this and to understand this, let me show you the chromaticity diagram, which is basically, it shows the color, the overall color, which is perceived from a certain light spectrum. And we can see that for the, for the sunlight, which is passing 100% through perovskite, we have an orange color, not too intense, while through the BG25, we have a very strong blue color. And with this 8:1 or 8:1, surface ratio, we can actually bring this this white dot here closer to the so-called Planckian locus, which is the curve that expresses the color of a black body radiation as a function of the black body temperature. Just as a reference, the sunlight would be more or less around 6,000 Kelvin. So here on the right, you can see what that spectrum looks like in more detail and its chromatic components. And what can we do to evaluate the quality of this light spectrum? Well, we can consider, for example, two important parameters, which are the correlated color temperature, the CCT, and the CRI, the chromatic rendering index, which is basically an index that tells you how closely the color of objects under a certain light spectrum compares to their color under natural sunlight. So in general, 3000 Kelvin is usually a good target for comfort, indoor comfort, while a CRI above 80 is generally considered to be good. And with this spectrum, that's more or less what we can achieve. So all is good, right? At least it seems to be this way. But why aren't we using this yet? There might be, several reasons, but the main reason, first and foremost, is, of course, stability. So, as is the case for perovskite every time, right? Here we can see the results of our experiments, so reliability under illumination. And we can see that after roughly a few hundred seconds, the current at maximum power point, and therefore also the power, start to decrease. And this results, or is the result of a fall in shunt resistance, as you can see from the dark IV curves, and from the light IV curves, you can see a fall in short circuit current, VOC, and most importantly, fill factor. And this trend continues throughout multiple experiments, so for a few tens of hours. Well, still seeing a decrease in ISC and VOC, and most importantly, again, fill factor. And this also occurs in low light conditions. So we have seen also that the extent and rate of degradation depends on light intensity. And just as a footnote, we have been seeing more recently that single cells appear to be much more stable and resilient. So once again, these stability issues are very strongly correlated with scalability issues, since these are results pertaining to mini modules. So, to conclude, I will summarize by reminding you what I've just talked about. So, FAPBBR perovskite modules can be employed in BIPV applications in conjunction with blue tinted glass in this example. And the indoor light quality can be assured and preserved by tuning the surface ratio between the two materials, without therefore sacrificing much area for the PV generation. So 8:1 surface ratio is actually significantly good. It's better than nothing, certainly. But these devices suffer degradation when exposed to illumination, which is not ideal, of course. And this degradation impacts mainly ISC, yes, but most importantly, the fill factor, which is the most related to power. And the extent and rate of degradation depend on the light intensity. So these things have to be addressed, certainly. So this is all on my side. I would like to thank my co-authors, my partners, my colleagues from Padova and from Rome, Tor Vergata and Chose, and thank the NEST project that funds my research. And of course, I would like to thank all of you for your attention.
Thank you, Noah. Very interesting presentation. I really appreciated also the effort to try to understand how this would look like in real environment, in a real building, a real application. So I have a questions. You mentioned that, of course, one of the main challenges for perovskites is the stability. So what's your plan and next steps to further try to improve it, and which are the priority in this perspective towards improving it?
Okay, so thank you for the question. First of all, I should mention we do not manufacture our devices. Our devices are manufactured by Chose. This is not to throw shade at them for their abilities, not at all, but what we can do is give feedback, right? We work on reliability, and this is what we do. So in our case, we've seen this is what happens, and we have tried to come up with some interpretations, at least preliminary, and there's a scalability issue. Cells are more resilient, the modules are not, and how are these modules manufactured? Well, these, for instance, are spin-coated, so it's not, let's say, the largest scale manufacturing technique, which still has to be optimized and achieved. And the series connection is obtained through laser etching, and that might be, let's say, a focus point for degradation modes. And yeah, well, certainly there is some optimization to be done. And but it's interesting that the single cells actually are fairly more stable in this regard. So there is a starting point. There is merit to using this kind of material, certainly.
Thank you again.
Thank you.
Let's move to the next speaker, Algirdas Baledantis from Modern Heat Technology in Lithuania. The title will be Implementation of Energy Active Living Environments through the Use of IPV Solutions. The floor is yours.
Okay, hello. Where can I change the slides? The green one? So this one? Okay. Okay, so hello everyone. First of all, it's a great pleasure to be in Florence at IPV conference. So my name is Algirdas Baledantis, and I'll be presenting company Modern Heat Technologies. In short, it's MET. And I'll be talking today about implementation of energy active living environment through the use of IPV solutions. So this presentation were prepared with the colleagues of mine from ProTech Institute. So let's begin. So we keep expanding solar farms, building larger and larger PV power plants, looking for more lands, but in reality is that we already have enough lands that we could use in our everyday lives. But the issue is we haven't made them energy active yet. So just look at the numbers. So we have urban areas, roads, buildings, and so on and so forth. But And these are really massive, large areas. We just have to integrate PV energy into it. So if we would look at the numbers, so in theory, if we would integrate a PV solutions only in 5% of that available area in our living environment, we would be able to secure power energy demands worldwide. And if we would look only for the buildings, so it would take approximately 82% of coverage of all the building available area, and we would be able to secure that energy demands as well. So, the problem isn't the available area or the lands. So it's all about the integration. So is it realistic? So, and do we have the technology? So in short, answer is yes. So we already, as in today, we can cover almost any available surface of our environment into the active one. So we can integrate our solutions into the roofs, which is the most obvious and most efficient point. Facades, second skin buildings, PV windows, IGU, canopies, and so on and so forth. The technology is not a problem. The real barrier, which I can see, is the mindset. So the mindset of architects, the mindset of construction companies, and so on and so forth. So they have to integrate these type of solutions into their everyday workflow, and to finally seeing the true value of these technologies. So please let me share with you a few of the demo sites which I picked up for every part of building integration. And I'll start with the facade. So why I have picked up exactly this facade. So in this particular building, in this facade, a PV modules were never intended in the first place, in the first design. This is a 300 square meter building facade area, and it contains more than 30 different sizes of PV modules. So this is a perfect example how our BIPV industry and manufacturing line and possibilities are flexible enough to cover almost every building facade or every area. So basically, we can replace any inactive elements with active one. So So this is a great example how PV doesn't have to be opaque all the time. So in this particular building, we had a problem. We couldn't place a PV modules on the facade due to the restrictions. So the only availability was to put a PV modules on the roof area. But since the building already had a skylights on the roof, and one of the demands was that we have to keep the lights to the building. So we came up with a IGU solution. So it was quite challenging because we had to, of course, there were a really heavy PV modules, and we had to keep a large gaps between the solar strings and solar cells. And due to the limitations of equipment, it was quite a challenge. Okay, so this is, I would say, the holy grail of BIPV installation. So this is a biggest BIPV roof, integrated BIPV roof in all of the Scandinavia. This installation uses nearly 10,000 units of PV modules. It covers around 7,500 square meters, with an annual output of almost 600,000 kilowatt hours yearly. So this clearly demonstrates that PV can replace a conventional building elements and even a standard PV modules without compromising and sacrificing the energy, performance, and most definitely aesthetics. And since we are in Italy, I picked up this demo site as well. Not demo site, but a project. So here's an architect wanted a functional shading system, although he wanted to use a surface for energy generation. So we came up with a replacement of a conventional shading fence with a PV module. So in this installation, there were almost 1,000 of units. And I know it's not mentioned, but it uses approximately 25 different sizes of PV modules. So the idea is to cover as much area as possible. And due to the long strings and long PV modules, the module had to be manufactured quite thick, and it was quite difficult as well. So, and this is the final solution of customization capabilities. So this is one of the products. So this is a combination of also conventional building elements with a PV modules. So the idea is not to put a PV module on the top, but integrate together with conventional building elements. So this is a metal roof laminated together with a PV module. And when you're taking this type of solutions, you're just taking a regular screws and you are screwing directly to the wooden battens, and you're using exactly the same installation as you would with a conventional metal roof. So installation is exactly the same. You're just connecting the wires beneath the wooden battens. And the areas which you want to leave not active, you just putting a regular metal shield. That's it. So installation is really easy. And maintenance is easy as well, because every day roof worker can easily replace these type of solutions. So with this level of flexibility, we can match any not active surface into active one. So either is a different color, a different thickness, different technology. Is it polymerik based? Is it glass based? If you need a really thick and robust PV module, or you need some sort of curvy PV module, we can adapt to a different surfaces of the building. It's not a problem. I mean, the technology already there. We just need to change our mindset. So to conclude, we have enough surface in our environment. All we lack is integration, and construction materials evolved into energy integration. The next step is scaling. So standardizing and integrating them into standard construction workflows for architects and construction companies. And traditional adds-on solar cannot unlock the full building potential. So thank you for your attention.
So thank you very much, Algirdas, for the very nice presentation, and also the portfolio of great examples of BIPV application. It was really interesting to see real applications. So one question related to your clients. So who are your clients, and especially which is the main driver you think led them to decide for BIPV rather than BAPV? So which is the main driver leading the choice for this kind of system rather than BAPV?
I mean, if you are looking purely to the energy side, of course, this cheapest option, especially considering the prices of current Asian products, you're just putting a standard PV modules and you are not looking further. I mean, if you are looking for aesthetics, especially heritage buildings where there is quite a few restrictions, you just have to put a not standard PV modules. You have to, the first choice is aesthetics. I mean, you have to replace building elements, but that building element cannot be different. I mean, active element cannot be different from the from the conventional building. For example, we have one of the EU projects, and what I learned, it was in Netherlands. So, for example, you are sending a custom PV module, and municipality compares that PV module with non-active element. And installation went good, everything installed. And after, let's say, few months after installation, one of the municipalities' workers drives by through that project and sees that your BIPV solution doesn't match exactly the conventional building element. You have to take everything out and replace the conventional building as well. So yeah, so especially for the heritage buildings, this is really important.
Thank you very much again, Agirdas.
Yes.
So I have the pleasure to introduce the last speaker of our session, Giorgio Pastore from Solitec in Italy. So Giorgio will share a case study on bifacial PV based on noise barriers in Lithuania. Thank you, Giorgio. The floor is yours.
Thanks for the introduction. Thanks, by the way, for the organization. Very beautiful venue. I am the last one, so I will be quick because I'm the last one before the lunch break. So, all right. So I will just give a quickly overview of the company that I represent today, Solitec. So basically, we are a European, North European company. Being manufacturer, producer of PV modules and energy storage system. We have significant market share in basically in North Europe, so in Baltics and in Scandinavian country, but quite strong as well in Germany and in Italy. We are famous for glass modules that are famous for being tough and quite durable, and also for the sustainability, how we produce those modules. So we are the first one, for example, producer who managed to get the prestigious sustainable certificate, Cradle to Cradle Gold. So a short story about our company. We are part of bigger industrial group called BOD Group, that in the 98 started the business in totally different business about replacement of CD. In 2000 and early 2000, we understood that this business was going to die. So we changed and we started to invest in the renewable energy. In 2009, we found Solitec. In 2013, we started our first cells production. Since that, the company kept growing constantly. Today, we are talking about integrated solution. And the concept is quite simple. Basically, we take something that has a specific purpose, in this case a noise barrier, and we integrated that with energy production. What we get is this that we call PV noise barrier, and that converts infrastructure that basically without modules sometimes is even quite ugly in payoff infrastructure that has a specific payback time. The motivation that runs our project basically is first of all because we strongly believe that the real future of PV industry is the integration of that, and especially in Europe, the land use of it will become more and more a problem. So this solution like noise barrier can solve partially that. Secondly, also in Europe, we have already quite strong infrastructure in highway and railways roads. So about 90,000 kilometers of highway and 200,000 kilometers of railways. So this makes those kind of projects scalable. On the right, I put the picture of Rail Baltica. It's a project about fast railways that will connect the Poland with the Baltic states, and basically is the starting point for us to thinking about this project. I will mention something more later. So some key parameters about this project. Our solution is a solution that, of course, can be done making by new noise barrier, but also installing on existing noise barrier. In 1 kilometer of noise barrier, we can manage to install between 600 and 3,600 modules that are translating into 0.2 megawatt to 1.3 megawatts, already certified according to European legislation for a noise barrier. This is the first pilot project that I'm presenting today. Is made in Lithuania on Lithuanian railways. It's a pilot project, so it's a small project, 75 meters, about 22 kilowatts installed. This project has been already installed 1 year ago, so we already have some data about the energy generation. And basically in 1 year, the reality of energy production beated the simulation that we did before starting the project. Almost every month, except for December and January. Winter in Lithuania can be quite tough. My previous Lithuanian colleague can confirm that. Imagine that last January in Lithuania, there was just 4 hours of sun during all month. So sometimes can be tough. Another pilot project is installed on the highway, on the Lithuanian highway that is connecting Vilnius and Kaunas, the 2 major cities. It's pretty much copy-paste project, so 76 meters, 20 kilowatts installed. And the energy use is being used for the local purpose, so lighting and information lighting board. Here are a few pictures of the installation. As you can see, the design is different. The reason is, first of all, because both are project integrated into existing noise barrier, so we needed to adapt on what we saw, on what we found. But this one helped us also to do some economical evaluation, so about the payback time of this infrastructure and so on. So the case one, about the one that we made on the Lithuanian railways, according to the structure, we calculated the difference comparing to a standard noise barrier is about 16% more, that in payback time get translated in about 5-7 years payback time. The second case on the highway, due to the gap, the bigger gap, the payback, the difference price is much smaller, just 80%, and then the payback time also is much shorter, in just 2-3 years. Going a bit more in details of the economical evaluation, we evaluate both the ordinary noise barrier and photovoltaic. And as you can see in the photovoltaic noise barrier, we understood that almost half of the price of all infrastructure is PV and B elements. So this translated into a difference of cost with about 105 euro per square meters, difference of cost between ordinary noise barrier and photovoltaic noise barrier. This difference, of course, is translated also into an infrastructure that has a real payback time in some years and not an infrastructure that will never pay off is the result. Being those projects a pilot project for us was very interesting also to evaluate the possible issue that those projects could face. So one question came out from the Lithuanian railways, and the question was if those structures could impact the radio frequency. So we made some tests basically based on vertical and horizontal polarization, evaluating cellular technology network. And what we found out is that basically, we compared the graphic, and we found out that basically in case of horizontal polarization, basically both noise barrier, the noise barrier, classic noise barrier, and PV noise barrier are working perfectly same. In the case of vertical polarization, we have different result, and the reason is due to the fact of the transparency, on the higher transparency of the modules. We are planning to redo the test now we are having also satinized module, so with less transparency, and we are planning to redo the test with those kind of modules. But anyway, this for the Lithuanian Railways company, those data were acceptable anyway for be used for that purpose. Another issue is the shading spots. So this is a possible issue when you install in something that it's already existing so that you cannot modify it integrally. So in this case, we had some spot where our modules were getting a shadow spot, and as we know, can be quite dangerous for the PV plants. On the right, I put the graphic of a classic graphic of how the PV modules installed vertically is working with the two classic hills. As we can see, in our case, in the second hills, we have a loss of power due to the shading. We solved this problem basically installing power optimizer. This is effectively solving the problem, but is of course also raising overall the budget of the project, and then of course also the prolonging the payback time. But in the long term is saving the project itself. Some future projects. So as I mentioned, everything for us started with the Rail Baltica, and we'll continue with that. The pilot project that we built on the railways roads is a testing project for Lithuanian National Road that is planning to build 1 kilometer of PV noise barrier along the Rail Baltica for a total capacity of almost 400 kilowatts. We have also another project still on the paper right now in Italy, nearby the Bologna train station, that should be about 1.2 kilometers, and for a total capacity of almost 470 kilowatts. But today I'm quite happy and proud, I will say, to share that we made our first installation, first pilot project also in Italy. We just recently, a few weeks ago, finished the installation nearby Rome on the speedway between Rome and Fiumicino. It's a 100 meters project for a total capacity of 20 kilowatts. Has been installed on existing noise barrier, so basically the installation was quite simple and effectively because we removed one noise panel and we replaced that with the modules with a special frame made by Soundsproof. All the work has been done in 3 working days, and this is effectively how those solutions can be done easy and can easily implement our infrastructure. We arrived to the end of my presentation. As you can see, I'm quite proud of the installation that we done in Rome, so I'm ending with a picture of that. Thanks everybody for the attention, and if there are any questions.
Thank you, Giorgio, for your presentation and the case study. You talk about some issues like electromagnetic and shadowing.
Yeah.
Is there a vibration issue also for this noise barrier?
The vibration issue, can be an issue depending on which modules can be used. The thickness of the modules is very important, and the frame that is being built around the modules is very important. Our modules are glass modules. One of the toughest currently on the market, so has high resistance on snow load and wind load. And the frame that has been built around with our partner Stalcorp, a Lithuanian company that do that, has passed all the tests for vibration test and wind load test. That it's very important in vertical installation. So yeah, I will say that problem could be a problem in case of using not glass module with plastic backsheet and so on.
Thank you very much.
So we reached the end of our time, but before closing, I would like to open to really one question from the audience. Let's see who is the fastest. No questions. So, okay, let me thanks very much again, also on behalf of Remy, all the speakers who were with us today, and thank you all the audience for your interest. And I would like to invite on the podium before the lunch break, Antonella Trombadore for an announcement. So thank you very much again.
It is a technical communication, technical information. Due to the interest to visit the pilot project in Santa Verdena building, we organized for tomorrow morning at 9:30 a guided visit. So you have the opportunity to see the pilot project with some much more details and also the big slab. But you need to put in the list. So in the desk of HETA, you can book for the visit. It's free, of course. Okay.
Hello and good afternoon. We welcome to our session, which is PV technology, manufacturing and sustainability. I'm delighted to announce our chairman, which I'm delighted because he's an old friend, which I haven't seen for the last 10 years. This is Dr. Hans Osenbreck, and he's a well-known personality in the PV world. For the last 30 years, we worked together in various meetings, and he's chairing this session. Thank you.
Ali, thank you very much, but this is too kind of an introduction of yours. Thank you very much. So, as I said, I'm Heinz Ossenblank. I'm trying to assist here based on my long-standing experiences in organizing programs of conferences. So I'm very happy that you're all here for the last session of this, I would say already now, very successful conference, focusing on PV technology, not only manufacturing, but also on the sustainability. You know, we have circular economics is on the headlines and many other things. And so I will introduce the first four speakers and then we'll hand over to Ali Saïk. So my first call would be for Jean Rondier from Wattway, France. And his presentation will be, now you have to see this, the first cost-efficient pavement integrated PV for electricity production. So I hope it's really cost-effective. Okay, it's your floor.
So, hello everybody. I hope you spent a good lunch. So my name is Jean Rodier. I'm working for Colas, and today I will present the first cost-efficient pavement in integrated photovoltaic for electricity production. So just a slide to introduce my company. Colas is a subsidiary of Bouygues, which is one of the top 40 company in France. They are basically working on construction roads and building material railways. And 10 years ago, they associated with the CEA and in particular the INES, National Institute of Solar Energy in France, so French specialist of photovoltaics, to make a great partnership that lasts since 10 years now on developing a crazy idea which is driving on solar cells. So you know basically about the context of integrated PV. If we represent so the cost efficiency according to impact and risks, for sure integrated PV has a lot of advantages. For instance, social acceptance, because we are using already artificialized surfaces. And of course, in terms of space management also. And if you think of specifically pavement integrated photovoltaics, we have other advantages, which are we are flat, so very highly integrated. We can, of course, we are not exposed to extreme winds. So we have a certain resilience. And another advantage is that we are using existing roads, meaning that the the LCA, the life cycle analysis, is quite better because we do not have concrete or steel structures for our modules. Of course, there are other limitations of those kind of solution, which we are flat also, meaning that we have, compared to an optimal tilted installation, some losses, around 40% in South Italy, for example. And we have to withstand traffic, and for sure our panel has to resist to the traffic, which means that we have an extra cost on this. So basically, the design of our solution is represented here. Our panel is directly glued on an existing surface, and on top of it, we have a glass aggregated, bonded by a transparent resin, and the system is directly glued on existing road. So the design is very important when you want to design an effective cost system, and for sure, we have to work on the three elements here, which are the balance of systems, the installation, and the panel. From the beginning, we wanted to make a panel that could be produced in standard production line, because the costs are better on those kind of lines. And of course, we decided to follow the cells and also the architectures of the cells of standard PV panel to enjoy all the cost decrease. We have a dedicated bill of material, which of course increase the PV panel price. So when you put solar cells on road, the first question is always the same. Does the cells resist to the traffic? How long does it last? We've installed around 100 of sites, experimental sites all over the world, in Dubai, Japan, Canada. And now we design a qualification test, which is quite basic because, of course, we have the ISE norm, classical. Our module passed the ISE norm last year, which was quite challenging already. And then we made some complementary qualification tests, impact tests. We have to preserve also the anti-skid of the system. So we have some specific norms based on road that we pass. So after 2 million wheel passages, our system was still very with a good anti-skid resistance. And we perform other tests, water immersion, and real traffic condition aging. So the two pictures that you see here are two systems that we use to qualify our panel. On the top, it's French installation, and below, it's Japan installation. And we successfully passed these two tests, meaning that now our lifetime is estimated between 15 and 25 years, according to the traffic. So in terms of cost effectiveness, we worked, of course, a lot on this because we talked about it yesterday and today. The integration and the penetration of the market has to be, the cost is still important for the people who buy, especially when you address a massive market where standardization is already here. So we, since the beginning, 2016, we doubled the power, the energy density from 97 kilowatt hours per square meter to right now 180 kilowatt hours per square meter. Of course, there was a cell performance that increased, but we also increased density. We adapt also the bill of material so that we can improve the transparency and also the lamination time. And now we are installing our system very fast because we develop our own machines to install the photovoltaic panels. And we are 10 times faster than we were at the beginning. As a result, we now reach a full system price below 2.5 euro per watt peak for a 200 kilowatt peak turnkey solution, which starts to be interesting if we want to address a large market. So the market we address right now, thanks to this level of price, for example, in Florence, we have a LCOE of around 141 euro per megawatt per hour, which is now completely competitive with the electricity grid price. And thanks to this, we can deploy other markets, and we will focalize on the market below, cycle lane, parking, forecourt, seaport, and airport. And just one example of the market, if you cover 10% of the cycle lane of Europe, it makes a market of around 8 gigawatt peak, which is quite important. And in terms of perspective, wetware is now a cost-efficient solution for electricity production. It's proven, robust, and IEC certified. We will continue to pursue improvement in performance and cost, optimization of stack, lamination, still continuing working with our partner INES on this subject. We are integrating now TOPCon in the specific module we designed. And our next target will be 100 euro per megawatt per hour. Megawatt hour. Thank you for your attention.
Thank you very much. As Jean was precisely in time, we could allow a question directly, but all the other more generic one we put at the end of the session. If there is one for the understanding right now, if not. Yeah.
The question is, what is your incentive having everything in the floor? Is it financial incentive, or is it more attractive that way?
No, we do not have incentive. I mean, the project that we are developing are self-consumption installation, so the energy is directly going on the building in general. But no, I mean, the idea is to maximize the self-consumption because we're not for the moment competitive with the grid, but we will work on it.
Okay, thank you very much. And I will move now to the next speaker, which will hold a presentation on the interconnection, encapsulation, and reliability for integrated PV technology. And the talk is given by Jonathan Govertz of EMEC in Belgium. It's your floor.
Thank you, Mr. Chairman. Also for the opportunity to be able to present my slides here. So my name is indeed Jonathan Govertz, and I will present on behalf of the Wafer PV team. It will be a bit broader, showing a bit what we've been developing in the last years related to integrated PV in terms of interconnection, encapsulation, and reliability. First, some background. We're from Energyville, and Jens this morning already gave some introduction, so that's nice. We are based in Genk in Belgium on a former coal mine site, so there's a bit of a link to yesterday where there was also the Scotia site, I think, where they are transforming a gas industry site to some nice place with renewable energy. And so here, the same, we have been doing this, and now we're located. You see the coal mine shaft there, still standing there, so it's a nice history as well. So as a team, we are looking at PV research, so going from sunlight to electricity. Basically, you transform the photons into electrons in crystalline silicon. In our case, we're focused on that. The animation is missing, I see as well. But so we integrate the crystalline silicon wafers into modules. Everybody is already aware of that by now, I think, with the previous presentations that we've seen. You see it can be implemented then as building applied on roofs or in utility scale. And we look at materials, process, and equipment to improve all these aspects for high performance, cost-effective, and sustainable modules. Okay, something went wrong here as well. But so, okay, everybody is aware here in the Integrated PV conference as well. So having building applied or utility scale PV sites, you could call them ugly. It depends a bit on your feeling of aesthetics, of course. But on the other hand, it's also a waste of land if you think about utility scale PV. And it's also, if you look at integrating them as a building applied on roofs, it's also a bit of a waste of material because you have and the roof tiles and then the PV modules on top. So it would be nicer to combine and to go for integrated applications like you see on the slide for vehicle, building, urban, agrivoltaics, and so on. So for this integrated PV, it means also you also have to look at the applications, and so you get more requirements than only the PV modules, and these requirements are then defined by the application. And so what I tried to do in the following slides is I listed a few of these, the most typical requirements that you can think of for several types of applications, and then give some snapshots of what we've been doing in our group to address these different requirements, basically. So one thing is one topic is the custom layout, and here you see, for example, is there a pointer? Yeah, so here you see a standard module, let's say, with based on stringing, and there you have these long strings of cells that you have to interconnect, and maybe you have to get lines to make them to the junction box if there are odd numbers of strings, for example. What we've been working on is what we call the twill interconnection technology. It's a multi-wire approach where the interconnection is integrated in carrier foils, basically. And this allows you to make turns all around, and it allows you to fill up the active area of the module as good as possible. And it also allows you more freedom in getting out the connections on different areas, so optimizing that as well. There is a video here. Sorry. Okay, it's not going to work, but this is a video just showing how it works. It's basically laying up a foil and then a cell, a foil, a cell, a foil, a cell, and so you can populate the whole area with to make it active with PV. We're working on this technology with some partner companies as well, and we have had some years in looking at this. So we developed the concept, and now we're in the stage of looking at automating and scaling up the manufacturing of this. If you apply this kind of technology, then you can also combine it, like we've seen in previous presentations, with colored glass, for example, and you can improve the aesthetics because you can reduce the amount of ribbons that are visible inside. You can also go for semi-transparent PV, like you see here. What we then also do together with our partners in Energyville, for example, KU Leuven, where we monitor the facade of our building, and we can implement different technologies, different module types, different interconnection types, and we can use these for validation for our energy yield simulations or for temperature calculations, these kind of things. So you can compare different, for example, this is the multi-wire interconnection that I mentioned. You can also look at back contact modules or shingling. All these things are possible. Another aspect is sometimes you want curved modules. And so for this, we are looking at a double membrane lamination technology that we are developing in our laminator. So instead of having flat laminations, we can also have a membrane from both sides, and that allows to make curved surfaces and even hollow surfaces if you play with the pressure. Of course, there you have to get the process right, that you get a symmetrical buildup of pressure on both sides to avoid still collapse of the module. And so with this technology, we had 2 projects running. One of them was looking at glass sunroofs for a car, for a passenger car. This is what you see on the left. And on the right, we had a project where we integrated PV this way, in this case, shingled interconnection into the bonnet of a car. Apart from curvature, also the weight is important, especially if you look at vehicle integrated for mobile applications. So if you look at the weight distribution of a typical module, so glass backsheet or glass, it's, as you can see, it's above 10 kilos per square meter, and it's all dominated by the glass, of course. So if you want to reduce the weight, you should try to remove the glass, and that's what other people also here have presented, of course. So you can think of directly laminating it on metal, like the facade panels that have been shown as well, or also on the car, like I showed in the previous slide. And the next step is then to also remove this metal, this aluminum or steel, and replace it with composites. And that's what we've been doing. So you can make the encapsulant, reinforce it with glass fiber or carbon fiber, or you do it in the back sheet. And then the last point is more on reliability testing. So we're all aware about the typical PV reliability testing for most people, and you've seen results from others as well. So you can do thermal cycling, damp heat, humidity freeze, very basic environmental testing, and that allows to look at, for example, here compatibility issues if you use combination of encapsulants, for example, and then you see discoloration in this case with a glass sample where it's coming from the edges as well. And you can combine these tests like what was done here in a project where Subsea had facade panels from Schweitzer. They were tested by with hail impact, and then we put them in humidity freeze. And so, for example, you see how in crystalline silicon, the micro cracks that were introduced by the hail impact are extended during humidity freeze due to the thermomechanical stresses that are implemented. If you do this on thin film approaches, in this case CIGS, you don't have as much impact of the hail impact because it's not a brittle material like the silicon. And in this case, there were some shunts before, but they were relaxed after humidity freeze testing. We also were involved in some projects where we looked more at the vehicle testing as well. And here you see, for example, a vibration test on the left that is done on the full bonnet, because there you need to see at the real product and test the real product and not part of it. What you can also do, and we did together with ISFH some tests in a project, which is a shock test. So basically, if you slam a door, for example, on a car, you get a shock impact, and it should also be able to resist that if you would integrate PV on the door. And then on the bottom right, you see a picture of a ball drop test. So in this case, it's a steel ball that falls on the sample. So there was a video behind, but it's not working as well, I suppose. So there's a ball of 200 grams of steel that falls onto the sample that you have to make, 30 by 30 square centimeter. And the test is a safety test so that the ball doesn't pierce through and cannot hurt the passenger inside. And there's also some requirements on the glass shards that extend, so the size of the glass and how it breaks, it shouldn't fly around. And so we could pass this with modules that we make. But in the first instance, there was also some concern because the ball was bouncing back relatively high. And you also don't want, if a ball drops on a vehicle, that you hurt somebody, a person standing next to the vehicle, for example. So for this, you need to play then with the adhesion of the different encapsulants to the glass, for example, to absorb the shock rather than to reflect it. And then finally, a final slide on partial shading. It was already mentioned as well in previous topics. So partial shading is a concern and can be a concern. So you need to take it into account. So especially for vehicles, so you have stationary, you have stationary shading, of course, in this case from the trees, or if you would have PV on the car, you would have shading, in this case, from the PV above it. So that can happen. And with a car, it will be parked in different spots. So the shading is not very predictable, let's say. So we've seen in other presentations, we've seen people from AE Solar looking at back contact cells to solve this, because then you have a, let's say, a bypass diode integrated in the cell. Yeah, just 1 minute. And then other solutions are, for example, the matrix shingling that was also presented yesterday to relax the partial shading issue. Let's say in our case, we were looking at the technology where we could use existing strings and have a separate fabric where we integrated bypass diodes per cell that we can implement during the lamination, and this way have one bypass diode per cell for a standard string, for example. And this we have been looking at. We've shown the concept, and we're in the process of upgrading it and also looking at it for different applications. With this, I would like to acknowledge all the projects that were involved and all the people that were involved, and thank you for your attention.
Thank you so much, Jonathan. I'm quite impressed by the amount of testing you're doing for typical problems which we face in integrating PV. So
we do it with partners as well. It's not
okay. Yeah. I think it's addressing the issues very well. Thank you.
Yeah. Regarding the car, PV car, how big your battery storage and how long the car go without charging?
In this case, we look only at the PV side of it. So that will be the next step to size it.
Very attractive the way you put the panel is so lovely.
Yes.
It looks like a normal car, and this is wonderful. If you have enough, charge to use it indoors or use it for, long distance,
Yeah. So one of the things, the aesthetics is very important. That was mentioned also for passenger cars. That's crucial. It's less so for trucks. Then you're more relaxed on the aesthetics. I think it's also important to look at the weight. If you look at cars in general, we need to reduce the weight of cars to make PV more important, and also the aerodynamic track, things like that. I think people from Lightyear yesterday were mentioning this as well.
Excellent. Thank you.
So thank you again. And we move to Xavier Otano of Mondragon Assembly. So we're moving in the manufacturing specialities. His talk is titled Innovative Tool Solutions for Manufacturing Solar Integrated PV Modules. So it's your floor.
Okay, so, okay, perfect. Thank you very much. So a little introduction about Mondragon Assembly. We are an automation company. We are more than 600 people worldwide, more than 150 million euro turnover on doing machines. What kind of machines we do? There should be a video running here that is not running, so that's going to be a pity because there were plenty of videos in the presentation, so sorry for that. So we are doing the video on the right, you should imagine. It's a video of a turnkey line made for a 500 megawatt line for standard modules, and the video on the left on the left should be a video of a standalone machine for labo applications. We will see them later. So a general idea, I think you all know ITRPV with their crystal ball of what the future of PV would be in the world. And they are saying something that we all know in this room, that IPV solutions that beyond the mainstream PV applications will be more and more important in the future. So we are talking about niche applications that could be gigawatt scale in the near future. So the idea is that on a mainstream module application, the only driver, it's the euro per watt peak idea. That's the main driver. But when we go to BIPV, floating, mobility, agrivoltaics, tiles, integrated PV in general, there are lots of other metrics that should be considered. Could be from watt peak per kilo, could be euro per beautiness, if we can call like this, if we consider the aesthetics, about the integrability, it's about robustness. So there are other metrics that should be considered. So we have found out that there is a kind of a development loop on when the projects or the new products are being defined. This should be running with a nice animation, but sorry. So someone is thinking of a new application. He thinks of how the module should be, what kind of a special feature this module should have, and he develops a technical solution. So, for example, on a BIPV application, it requires something to be aesthetically pleasant, and the modules that should be developed should be colored modules or different distances between the cells and the strings. So this loop that is going, let's say, from left to right, it can go back from right to left, because when someone develops a module that has a different string cell distances, it appears a new feature on the module that it gives a different grades of shading on the module that can be used not only for BIPV applications, but also for agrivoltaic applications. So the innovation loop, it's closed in this way. It's application, feature, technical solution on the module, and it can be seen that this same module can be applied to different environments. Of course, it's not direct. There should be some fine-tuning on what it should be, what it should be done in each of the modules. But all these would be to develop the solutions at module level or at application level. But someone needs to build the machines that will be doing these modules. So when developing a new concept of a product, it's very important to take into consideration how the manufacturing of this product will be. And there is where people manufacturing equipment, we enter in the game. So here are some examples of Mondragon assembly equipment on different projects. So this is a project we built for a company that is doing BIPV modules, where they were asking to build modules going from 300 by 300 millimeters, so it's very small modules, to 3 meter by 6 meters modules, very big ones. Very small batches, unitary batches. In this case, if you are building 3 modules the same size, happy day. And a very wide variety of string configurations on the module. So it could be 0 degree, 180 degree, or even in 45 degree angles. So we developed specifically for this project a specific stringer that could be doing this size of strings with the adjustable gap between cells and adjustable gap between strings. A very specific layup system to put those strings on the glasses and to be able to reach any position on the glass with the right angle and the right spacing. And of course, we also developed all the testing equipment needed for such kind of module for the EL tests for such small and big applications. We also made another project as an example for someone that is building light and flexible modules, very flexible. So in this case, these modules are glassless. If you think of a module manufacturing process, normally we lay the glass, we put the first layer of encapsulant on it, and we build the module starting from the glass, sunny side down, to the back. That's the way a normal module is, a standard module is built. If we have a module that is glassless, you have to imagine that there is no glass, so the module cannot be built from glass to the top. It has to be built somehow. So we have developed a line where there are some kind of carriers that act as the rigid layer, and we add different layers on top of this carrier. For example, one specific thing that has to be developed for this kind of applications is when you do the trimming of a module. After lamination, there is an excess encapsulant coming out of the glass. You need to trim this excess encapsulant. On a standard module or on a glass module, it's an easy thing. You go with a knife against the glass and you cut it. On a glassless module, there is nothing rigid that stops the knife. So instead of using a standard solution for that, we need to develop a solution where the trimming is made with a CNC system and with a robot handling this flexible module. This is another example for another customer that was also willing to build a module glassless. So in this case, this customer, instead of building a flexible module, it's building a rigid module, but very light. How does it do it? It's using a honeycomb polymer backsheet or backplate, and as the base substrate for the module. And in this case, instead of building the module sunny side down and going up layer by layer, we have to start from the back sheet and we have to build it sunny side up. So it's a simple thing, just you build the line with the module tilted over 180 degrees. It seems a simple solution, but you need to build a laminator that is upside down. You need to build an interconnection machine that is upside down, and you need to build a lot of standalone machines that have to work upside down. So we developed this kind of solutions for this customer, and you can see the nice video of the line there. Then other examples that we also developed is we have done a line for space applications to build the modules that go in the satellite, modules for very harsh conditions. And in this case, it was a solution for a crystalline silicon cell, but with very odd shapes. So if you look at the stringing process, concept-wise would be the same as in a standard module. It's a connection front-back, but the reliability that is needed and the size of the cell and some of the operations need to build specifically for this customer. Other project we built is the laminator you see there. It was for a hybrid thermal and PV project, where a thermal plate is attached to the backside of the module, and you have the thermal solar module where you heat the water, and a PV module on the front. So there was one presentation before. I cannot remember who did it. A lot of names, a lot of presentations. But talking about the thermal expansion of aluminum plate when you are doing the lamination on an aluminum plate. So this is exactly that. It's an aluminum plate that is laminated together with the module. And on the presentation, it was explained the thermal expansion when running on the field. Here, we are doing a lamination that is at over 150 degrees. So at 150 degrees, the expansion coefficient of the aluminum plate and the glass is completely different. If you do a standard process, you will have a flat surface that goes into the laminator, a flat surface that will come out of the laminator, but when it cools down, you have a potato chip. And a potato chip is not what you want to put on your roof. So we developed a system, a specific laminator that could allow to load something that is not flat and unload something that would be flat. So that's the kind of developments that need to be done on the equipment to build some special feature modules. And then we have been also involved in some vehicle-integrated photovoltaics. You have seen here some examples. There, the pretty obvious one, it's the curved surface of the glass. In that case, everybody thinks on how to laminate. That's the big problem. Yes, we can solve it. But nobody thinks that laying a string on a non-flat surface can be also an issue, because we want the strings to be really well aligned to be able to then do the interconnection. So doing that on a flat surface, it's easy. You go very, very close to the glass and you drop it. But when it's bended, you need to be as close as possible. But this curve makes the thing that can move when you are laying the string can move in any direction. So we have developed also solutions for this kind of laying down strings on curved surfaces. And we also build the equipment for what we call the mainstream to be. So I've talked about special applications, non-mainstream applications, but then there are a lot of people working in new cell technologies, AGT, TOPCon, perovskite, tandem cells, or new connection ways, back contact, IBC, XBC, front back, shingling. Everything could be welded, soldered, or ECA. So we also developed the equipment for that. We have made some machines for industrial applications, and we also developed equipment for lab applications. We have a machine. This is the multi-tool stringer. It's kind of a Swiss knife. You don't want to eat a bistecco fiorentino with a Swiss knife, but I'm finishing. So this tool, it's not the perfect knife for eating a steak. It's the Swiss knife. You can do in the same tool, back contact, front contact, ECA, soldering, shingling, induction soldering, IR soldering, everything at a very low speed, but very different technologies can be tested on the same machine. So in the same way we have built this machine for the connection technology as a stringer, we have also a laminator that can also integrate different technologies and different ideas of on the process. So long story short, there is a huge opportunity on integrated PV. The driving factor for the integrated PV is not the euros per watt peak. There are other things that should be considered. These standard modules need to be redesigned to be applied for these applications, and these new features bring new ideas, and equipment is totally needed to make this at the right scale and the right cost. Thank you.
Thank you very much indeed. And there's no doubt that Mondragon is part of the Seamless project. Okay, thank you again. And so I would like to call the next presenter. We make the question then at the end. And so it's my pleasure to call Yu Yao of Sunwell Power China, which will give us quite an insight how we make custom modules in China. And her talk is titled Tools and Equipment for Bridging the Manufacturing Gap Between Lab and Fab. So it's your floor, Yu.
Thank you, Chairman, for the introduction, and good afternoon. It's my second time today on stage. So this time I'm going to talk about our equipment division, what we do. Mainly, actually, we do on cell process development, a turnkey solution we developed for copper plating. And since we have also this customized module fabrication fab, we also develop some tools for this fab. And since I myself, during my study in Sydney, in UNSW, making the solar cells in the lab, and then moving to Switzerland, working in Meyer Burger, making some strings, we went through the one cell soldering station to a production machine, and also seeing how our research partner at that time making modules in their labs. So that brings me to the topic today, what we can do to bridge the manufacturing gap between the lab and fab here. And I think it's important because every product, when it goes from the R&D to production, it's from 0 to 1. And before it's 1, before it's 100, we can contribute something to make the 0 to 1 process easier. So our company, I showed the front facade in my previous talk. And here is actually the building where we have the factory behind. The office floor is 9 floors. So this is under construction. We are going to move into this building end of next year. So the equipment division, we have more than 100 engineers, more than 300 patents. Currently, the manufacturing area is more than 8,000 square meters. And for the machine part, we have a lead time design to delivery less than 12 weeks. So what we have done in the past, we have covered basically these 4 categories of equipment: patterning, plating, and also some wet bench. These are all for production. And inspection tools, the photoluminescence for tandem device. This is our second model is out. And the 3D line scan profiler, which is actually for in the electric cars when people are trying to. So in solar, we move away from silver to use copper because copper is less expensive, it's a similar level of conductivity. And in electric cars, actually, people are moving away from copper to aluminum because it's lighter and also cheaper in terms of dollar per kg. And so I will quickly run through the equipment. This is the first lab tool with it's a laser direct imaging tool. So basically you can, in a CAD, to put in the drawing you want to have for the solar cell, and the LDI will just project the image on the solar cells. And then this is our production version, 7,200 cells per hour with the the linear motor, so the stage go up and down like the direct motor. And our lab tool for electroplating, several tanks, we can go through the copper plating process and rinsing and drying. And this is then the production plating tool, 600 megawatt single tool, a multi-lane vertical plating. And the wet bench. So yesterday we had some discussion about the net zero building. Actually, which has a lot to do not only with PV electricity generation, but also the energy efficiency. And actually in the wet bench, we also implemented ways to improve energy efficiency. By changing the way how the wafers get dried, actually per gigawatt, we can save 1,000 kilowatt hours per day, the way we're doing the modification in the production line. And this is the lab PL. So in module manufacturing in the lab, typically we can see all these men and women doing the soldering, layup, junction box mounting by hand. And in a fab, like the gentleman before me from Mondragon presented, typically a production line more than 400 meters long can cover many automatic process steps, but they have limitations as to the number of solar cells, the technology, how many bus bars, the format of the cell, if it's glass backsheet, glass, what would be the throughput, and also glass size. And so where are the gaps? It's a non-standard size of glass we have from typically IPV modules, different cell dimensions, string length, and it's a relatively small volume, but many varieties. So it's quite difficult in the early stage to justify an investment in a machine, because the machine cannot be really fully fixed in the design as to what are the products that will go through the machine. So it's a relatively low ROI for the investment, and it's a complicated machine to build if we just want one machine to deal with all the different customized dimensions. So I give you some examples what we do in the factory. For example, when we have a standard stringer, which you can take some time to modify it to make strings with 5 bus bar up to 20 bus bar by making some changes in the existing machine. The way we adapted our existing design to produce strings of much smaller size cell and much bigger gap is we add a loading and unloading station, so that for example, when the gap is really big in an existing stringer, typically you would have problems like the cell is too small for the vacuum suction. And during movement, it's not staying in place with respect to the positioning of the ribbons. So we put a very small slice of cell together with a dummy wafer. And the dummy wafer is used to help in the transport of the string. And the dummy wafer is then unloaded after the string is made. So this is then the work done by our equipment division for the module manufacturing division. And we also make layup and autobusing, but it's for a small string, for example, just a few cells, but we do it with precise control of the positioning. So the robot arm can pick up the string, take an image, find the centering point of the string, and then move on to the autobusing station. After finishing the autobusing, it then makes the string on the glass in certain locations, and this is quite precise with the vision control and the robotic arm. And we've also made, for example, a volume product. We say now we make, it's kind of a fixed dimension product, but you can see the interconnector has a special angle of bending. And in the past, we do this by hand. So we draw on the template where we should place 2 interconnectors, where we should make the soldering. when we have fixed the design of the interconnector, then we build a machine for that. And this machine also can put the tape on the interconnector as where you want it to be. So these are the examples. And I just want to say with what we did up until now, so during our manufacturing process, we try to provide always solutions to the problems as we see them. And today, the products, beyond the standard format, it's trending towards machinery with more flexibility for customized designs. It's more like our 3C industry for consumable electronics. There are a lot of brands. Each brand comes with some sort of special design. So the 3C industry is actually, the machinery for 3C industry is actually constantly building new non-standard machines. And with the coming, the picture I show on the right is actually a new model from Unitree, where they replaced the human foot on a humanoid robot with a stage that can rotate, but also houses a battery there. So the robot can work for longer compared to the human robot. And we in China, we embrace the coming reality of this robotics plus AI. But here we think before that's really coming into mass production, we still have some work that can be done by human-generated machines. And that's concluding my talk. Thank you.
Thank you very much. As usual, very impressive what you're doing in China. I'm happy that you still embrace human work.
Yes.
Very nice. So thanks again. I will hand over now to my co-chair, which will announce the next 4 speakers. So Ali Saik of the World Renewable Energy Council will take now from here onwards. Thank you again.
Okay. Now our next speaker is Eftichia from Greece. She's going to talk about step towards industrial mass production of semi-transparent organic photovoltaic for buildings.
So I am here in the place of Evangelos Makeridis. He's the main engineer and the CTO of OET, which unfortunately he couldn't be here, so it's his presentation. I will try to do my best in order to present in his place. Yes, and we're going to talk about this new organic photovoltaics, the semi-transparent organic photovoltaics, and how we are stepping now from pilot lines and from the laboratory to mass production, since we have already done some tests and we see that these are working quite well. This is the journey a little bit and part of the project that we are working on. If some of you were here yesterday, you would already seen through my presentation. I am the innovation manager of HOPE, Mrs. Martinidou, Eftichia Martinidou, like I was very kindly introduced. And my association and OET, the company that I'm presenting today, is part of the Flex to Energy project, which is a European project that brings together 18 experts from the whole Europe. Mondragon is among them. I was surprised to see one of the representatives here today. For the assembly and the robotic line. We also have a partner in Coatema, Stellantis and CRF, the Center of Research of Fiat, that is helping us a lot with the life cycle assessment and with the integrated vehicle photovoltaics. And we also have INCOR and IPC in France. We are helping us with lasers and with the recycling part, because organic photovoltaics are 99% recyclable, so we are working really hard into this as well. And of course, partners back in Greece, Stepia, which is in the automation, OET, which is the company I'm presenting today, which is the spin-off of all these innovations, Alumil and many other experts in the field of integrated, let's say, integration of all these cutting-edge technologies. And here is what we want to talk about today, what Vangelis wanted to talk about today. It's the world's first manufacturing line for robotic, manufacturing line for organic photovoltaic systems. It has an automated assembly machine where the lamination will be happening, and it has a roll-to-roll printing machine where the organic photovoltaics would be made. They're made in atmospheric conditions, and that's why we have a very low carbon footprint when we are producing those. And today, like with the pilot line that we have, we can produce around 20,000 square meters of organic photovoltaics. We have done some demos with this. I will show you later on. But with this new line that will be fully operating by the end of next year or the beginning of 2027, we will be able to have a capacity like almost up to 1 million square meter per year. You know the generations of OPVs I've mentioned already yesterday. We are in the third generation. We are exploring perovskites and organic photovoltaics. For 35 years, we are in contact with the LTFN Research Institution. It's a nanotechnology institution back in Thessaloniki. And over the last 35 years, they were able to stabilize and bring in the market, in a small market though, because we're talking about a pilot line, so we had a few customers and selected customers up until now. They were able to brought the organic photovoltaics. They are semi-transparent. They have a very like an enormous freedom of design because it all depends in the breeding strategy, and that's how we can play with efficiency as well, because depending on the transparency, it's also the efficiency of the watt that we can do by square meters. There is a variety of color, and also now with this new assembly and manufacturing roll-to-roll printing line, we can also have different shapes of the product because up until now we could only produce 0.3 centimeters up to 1 meter in diameters. And yesterday I talked about agri-OPVs, organic photovoltaics. I'm an agriculturist myself, so we have done some research as part of the program. But today I will be talking about building integrated organic photovoltaics, and also another field that we have been working a lot with the CRF is the vehicle organic OPVs. Here you can see a Ducato and some other integrations that they have made. And so many speakers before me spoke why it's so important to move and have like some changes in regulations, also some help regarding how we can integrating photovoltaics in buildings. There is like larger surfaces. We see that there is the total consumption nowadays is around 40%. Is on buildings, especially in Europe. We see that many of those buildings are old buildings, so we need to find a way to upgrade them energetically without, however, changing their facade, or there are like many legislations regarding all this. So a lot of the buildings here in Europe, they need partial or deep renovation in order to be more energetically in line with what we want to achieve. And some benefits of the BIPVs in general, and the organic PVs, more certain when I will move with the spectrum band. So we know that it's not just about energy generation. They are very well into cooling down. So we have heat reduction when we use them. Is the shade provision, which is important depending, of course, when you are. We're coming from the Mediterranean. Country. Northern Europe is a different thing, but in general, we see that it can integrate many of things that we like, also cost savings. And the interesting thing with the organic photovoltaics being flexible and everything, but being also semi-transparent, is that they are able to filtrate somehow the radiation that pass through. And we saw that with the agrivoltaics and the experiments that we have done before that. So they allow certain, for example, the PAR radiation, which is the photosynthetical active radiation, to pass through, and that is good for animals and for plants and also for our humans, while at the same time they can block the IPR radiation and the UV radiation to a certain extent, because that's how they regenerate energy. And like there are so many wonderful experiences done by our physics teams back. I am not the most qualified to talk about this, but it's just a general idea of how they are working and why we see them as quite useful to integrate in our facades, in our buildings, in our windows. And here are some of the applications that we have made, some of the work that we have made. We have this energy windows aspect. Either they can be in the window or retrofitted in already existing windows, depending on the customer and what they're asking and what they want. The transparency is 50%. And we also have the curtains, which was like an idea some time ago from an engineer, because in case that you don't want your whole window to be retrofitted or having like organic photovoltaics. And of course, they can also be retrofit or in pergolas, already existing surfaces, because that was an issue, especially when we were working with the university. There was a demand to be flexible regarding that and be able to pretty much stick them everywhere and produce energy from every surface, already existing surface. They are very lightweight. They weigh less than half a kilo for 1 centimeter. So that's exactly why we decided to put them in surfaces that they cannot hold the weight of silicone PVs. And that is some examples that, for example, for Façade, for a famous hotel back in our city, and some stations and park roads and everything, those that couldn't like hold the weight of silicone PVs, for example, this gas station here, they wanted to integrate photovoltaics, but unfortunately this structure here was like, it couldn't support even the weight of like an adult human. So they reached us and asked us if we could do something about that. And yes, these are some of the application, retrofitted application, most of them. And here is an example of a bus station that the municipality in Greece asked us to develop for them. Thank you very much. I will be happy to answer any questions. Unfortunately, I'm not the most sufficient, but I have also here the email of Vangelis, and I will be very happy to connect you with him or any other from the team of OET if you have more questions or questions that I cannot answer myself. So thank you very much for your time.
Okay, our next speaker from Germany, rethinking solar. The rise of vertical bifacial PV.
Yes, thank you a lot also for having, thanks a lot, for having the opportunity to speak here today, for all the organization. And I want to talk a bit about a bit different topic. So again, I talk about IPV and also like stated here, rethinking solar. I think we saw it during the conference a lot, that we need more smarter solutions. We need, innovative solutions, also maybe not the most intuitive solutions. And maybe one of them is vertical bifacial PV, or in general also vertical PV. So first of all, I want to show some projects which use vertical bifacial PV. So for example, one of our projects, which I'm later going to talk about again, is at the Frankfurt Airport, which is a PV plant of 17 megawatt peak installed power. But also a presentation we saw earlier today was that vertical bifacial PV can be used for noise barriers, or also here another project in Germany, which is vertical floating PV. So in the case of floating PV, we can also use vertical bifacial PV. But then, like somebody earlier asked me at the stand, like, why should we use vertical? It's maybe not the most intuitive case to use it. Like, why not use it tilted? So first, like how we do it at Next to Sun, which I'm representing today, is like we use PV modules in landscape orientation and stack them over each other. And then we have like multiple rows with a certain row distance in between, especially if you talk about IPV. And then we have typically an east-west orientation. And how do we tackle like that we have two orientations actually is that we use bifacial modules, and in case of our case, like high bifaciality modules, up to 95% bifaciality. And in the end, what is the purpose of it? Why is it good? One big advantage of is actually the production profile. We saw it also earlier with the presentation about the noise barriers, that we have a different production profile that we actually have when we have typical South PV. So we see here in the graph in blue the typical curve of a South PV installation, and in yellow the production curve of a vertical bifacial PV installation. And there, also in gray behind, I don't know if you can see it good, but it's the electricity spot market prices we had here for Germany for this sunny day. So we see that we actually produce energy when it's more needed, or when prices are higher, so in the morning and evening. And on the other hand, we have the dual land use, which is also tackled here in the IPV. So together with Agri-PV, you also have this dual land use to use existing area, and therefore this concept is also a good one. So also yesterday, my colleague was talking more about agrivoltaics, so I'm talking more about the general concept. But in general, what we do is like I said before, have these multiple rows, and then we have this biodiversity strip underneath the rows, which can be used for biodiversity measures. My colleague talked about that yesterday. And in between, we have the actual crop strip where we do our crop yield, where we plant our crops, and where the farmer uses his machines. We can, of course, adapt that row distance so that the farmer can use his machines and has the width of its machines, because it has to also be efficient. Because I don't know, if, for example, if your machine would be 8 meters and the row distance is 10 meters, then you would always have to do 2 turns, like one time with 8 meters and then another time just for 2 meters, which is a big impact for farmers, that they don't want to do that. They want to be comfortable when doing the farming with their machine. So this being adjustable is a good concept. And yeah, like I said, and also another big pro of our concept is that we don't use concrete or anything. We just ram our post into the ground. So it is also removable if needed, and also we don't put concrete or anything into the ground. And yeah, this results actually in around 90% or even more than 90% of the area still being usable for agriculture. So we actually just lose 10 or less % for PV production, and therefore we have a possibility to combine these two economies, so agriculture and energy production, which in some cases tend to conflict. We have these land use conflicts where farmers have to concur with PV installations, PV plants, and therefore this is a good solution. Now I want to talk actually about projects we did. So this one is a project we had in Germany, in the Black Forest. And here also interesting is actually the story behind, like I talked before, about the land use conflicts. So this is an area of around 11 hectares, which is used by a local farmer. But actually the local farmer is not the landowner, but he did his farming there. And in his first plant, the landowner was planning to use a conventional South PV, or conventional PV plant, which would have led that the farmer lost all this land which he before used for farming. So a typical land use conflict. But what happened is that the farmer, together with us, actually was able to convince the landowner that this agri-PV concept is good, so the farmer can still use the land for agriculture, but he can also make benefit, also economic benefit of PV production together. And some key facts, so it's a plant of 4.3 megawatt peak installed. It's also a combined plant, so we have vertical, but also South PV, which you see on the left corner. We actually have a higher row distance than typically, so 30 meters or more, because the farmer has pretty wide land machines. And because of that, this is actually one of the world's first vertical PV systems with 3 modules on top of each other. I don't know if you can see it in the picture, but it's 3 modules on top of each other. And this was needed because we have a larger row distance, so we would have less installed capacity per area. So, but then using 3 modules on top of each other, we kind of get the same specific installed power per area that we would have with 2 modules on top of each other and a row distance of 10 meters. And here's some impressions from the production. So here, how it is built, or how a system is built. Also then the finished rows, the 3 rows on top of each other in a snowy condition, which is also a benefit actually of vertical PV, that like when having snow, maybe not in Florence, but in Germany in the Black Forest we have it sometimes. We have a high albedo, which leads to higher yields from this vertical bifacial plants. And then last, like a top view, again in snowy conditions, where we also see an advantage for this case. So if you look on the left, right, you might see under the snow, south PV tilted, and then our system, the vertical, which is not covered by snow. And also yesterday, as my colleague said, soiling is less of a problem. Coming to another project, which was a Fraport project, so at the Frankfurt airport, a PV plant next to the runway. And there, this VBPV concept was actually optimal because on the one hand, like because of the reflection, using tilted PV would actually not work there because reflecting would lead to disturbance for the pilots. So vertical concept is actually optimal in this case, and also maintaining biodiversity, because actually these runway strips next to the runway have a high biodiversity or special biodiversity. And here together, like this AgriPV concept combines these 2 aspects perfectly. And this resulted actually in an area with a length of 2.8 kilometers, so like along the whole runway. If you ever fly from Frankfurt, you actually see it. And it's also the largest VBPV plant with a total installed power of 17.4 megawatt peak. And then also another big topic I want to talk about is revenues and profitability. I think it was addressed in some times that like cost is important, revenues, profitability. And what we see right now in the European market is that we have negative electricity prices, we have low solar market values, we have cannibalization of PV. And here, our concept has also another big or important advantage to conventional PV. As I talked before, we have a different production profile. We produce in the morning and evening, so when prices are higher. And here seen in the graph, we have for 3 of our plants we built for each month of the year, the difference of our market values to the solar market value here for Germany. So we see for each month we have higher market values, and in summer up to 45% higher market values. And this was for 2024. And also here the yearly profile values. So comparing the yearly profile value we have per megawatt hour for general solar and our solar energy production. We see that we have, for example, for Wellingen, which is in Western Germany, we have more than almost 30%, 28% more market value per megawatt hour, which is a big point, and I think is also something maybe building integrated PV, especially for facades, can work with, that we there have the possibility to produce energy when it's needed, and also make more revenue and have more profitable solution actually, even though if you might produce less energy, we produce it in the times when it's needed. And as I said before, this comes from the demand-orientated production profile due to the east-west configuration orientation. So to summarize it, the VBPV concept, for example, with AgriPV is like also a perfect addition to existing electricity infrastructure. For example, if you already have South PV, you can just add up VBPV and then flatten out your production profile, that you not only have the peak in the midday, but also in morning and evening, because we have the demand-oriented power production. And further, we have the minimization of land use conflicts when using the AgriPV concept. Furthermore, as I showed before, we have existing projects which show actually the scalability and feasibility of this concept. We have projects with up to 17 megawatt peak installed. we showed it's working, we show that it's profitable, and we get revenues, which are also for investors, advantage. And yeah, as I said before, the higher profitability, which we also calculated here. I'm almost finished. Calculated for 2024, we actually expect it to even increase in 2024 because the effects of negative electricity prices are even more. We have now storage, but this system is even more profitable without storage, and it can also be combined with storage, and then you have also higher revenues. Then I would thank you for the attention, and yeah, thank you for inviting me.
The next speaker is Ms. Alexa Rosenberger, again from Germany, and the talk will be resource efficiency with building integrated PV in construction.
Thank you so much. Yeah, I will make a little journey on a higher level, not too deep inside the production of PV. I will go on a meta level, on a little journey on a meta level with you, please. So we will go back. We have to talk about global material consumption, and we have to talk about the big block of non-metallic minerals, because this is construction materials we use. And there is a direct nexus between climate change and global material consumption. And it's not only fossil energy that causes CO2 emissions, it's the extraction and the use of materials. But we didn't focus on that because it's not part of the main focus we all have in Europe, especially in the construction building sector, on the B level, on the using phase of the life cycle analysis. But it's A, and A is more important because that is the biggest game changer we have to reduce CO2 emissions in the building and construction sector. The material use or the OECD mentioned that the global material use, and especially the non-metallic minerals, the construction minerals, will double up to 2060. And this is also one of the points because that we didn't reach the 1.5 degree climate target, and maybe also the 2 degree climate target also. We can't reach it if the material use will double in future. So this is China. I'm sorry, you. This is China. China needs in 2 years from 2011 until 2013 more cement than the USA in the whole 20th century. That are the dimensions we are working in the construction industry. That's the biggest problem we have. And we run in scarcity. We run in scarcity with many other construction materials. And so we have to focus on these materials because these are the game changers. Yes, I mentioned it out. Let us take a look on the LCA. The LCA we use in the building sector has some problems, and you see the biggest problem here because it was developed for short-running products and not for long-lasting buildings. And this is quite a big problem because we are looking on the LCA and calculating all emissions over time of 50 years in the average in Germany or in Europe. The problem is we do not have any idea what happens in 50 years. So I will give you an example. This is a fantastic building that was built in 3 years ago. It got many prizes, sustainable prizes, and so on. And it has a big PV plant on the roof. And this was one of the sustainable buildings in Germany that ever been built. And the architects made it very fantastic. It was completely dismantleable. It has a digital twin. It was completely perfect in the construction, also to rebuild it again. And then today, and this is a game changer, I think this happened. So this building was a showroom for furniture. And the whole area was sold to an American investor. And he used the PV plant. This is now on the new logistics center built up in concrete. And the whole sustainable building is gone into a thermic use. So, and this is a game changer in Germany because we can't see in the future 2 years, like this building, nobody expected that it was crashed until 3 years of use. So we have to think about, is it okay that we calculate phases like B, C, and D in the ACA? This is a big question because it's not a reality. And this graph shows you that, for example, in 2040, we will plan Moon Village, or everybody who had seen Star Trek knows that in 2067, the warp will be found. So we do not have any idea of what happens in the future. But we calculating benefits, for example, for CO2 recycling of materials and so on in 100 years. And this is a big mistake. And this is why we don't get the emissions in the whole construction site down, because we just make fake calculating that makes it nice. So, and come on. And for me, it's like reading coffee grounds or look into a crystal ball, because 50 years ago in future, nobody knows what happens. The biggest problem, especially with recycling materials and so on, is material will be recycled if there's a market. If there's no market, we will never have its recycling. And that was also the problem with the destructed house. There was no market for these used materials. And if there's no market, nothing will be recycled. And that's the biggest problem we have. So, in fact, we have to quit if we want to really calculate the value also from the CO2 and in the ACA. We have to quit all other steps after A5, after finishing the construction or the renovation or the modernization of a building. All other things are just, dreaming, I think. So, and this is the main point. The only emissions we really know are A1 up to A3, and all other things we don't know in reality. And this is also a question we have to talk about the PV. But what in the resource efficiency of the construction materials, these things are more interesting. It's not the emissions of the PV plant from an A1 until A3. It's the emissions of the materials we don't use, using integrated PV for facades and also for roofs. And so reducing is, when I take a integrated PV facade, for example, I can, for 10 square meters, I can reduce the emissions about 700 kilograms CO2 because I don't need facing brick work, for example, or I don't need a certain wall of fiber cement. I don't need sheet materials, and I think these are the most important CO2 emissions we don't bring in the atmosphere. So the PV plant, and this is in the best place, is I can bring it in a recycling process, and it's an active, and I love this word, it's an active construction material, so it produces energy. And it's not an inactive or a kind of dead material like fiber cement or anything else that could not be recycled at the moment. And this is the parts we have to think, what could be, what don't we need, what we do not need in the construction. And this is, for me, the important point in the integrated PV discussion. So we did it also for the roofs, and you see a 10 square meters roof in the best case. We don't need roof tile. This is they're high intensive from the energy demand. And also we can separate 150 kilograms CO2 per 10 square meters by using an integrated roof PV. And I think this is on the remarkable values we have to keep in mind in the construction site for architects, for planners, because these emissions we couldn't get back out of the atmosphere. So that was my presentation. Thanks.
Thank you. The last speaker is Ashta Secondina, Politecnico di Milano, Italy. Circular Manufacturing 5, Human-Centered AI-Aided Digital Framework for Closed-Loop Photovoltaic PV Production Value Chain, CIRCMA 5. Please.
Good afternoon, everyone. I'm Ishita, as mentioned here. I'm here on behalf of Professor Niranza Georgi. We are actually a group of architects, and we are a part of this project, which is Horizon. Okay. How can I change this? Okay.
Now we can speak.
Okay.
Yes, better.
Okay. So I'm here on behalf of Polyme team to present this project, which is the Circman project. And what I'm going to be doing here is basically representing a part of it, introducing you to what the project is and what role did Polyme play in this. So just at a glance, it's the project under Horizon, another call for 2024. And it's a 36-month project starting from the 2024 of September. And it'll end in 2027 August. And it's coordinated by CERT, which is based in Greece. And it includes 19 participants from the various countries of the European Union, in which we have 7 research centers, 6 industrial companies, 1 non-profit organization, and there are 4 end users representative, meaning like the project which is being researched upon is going to be implemented and being tested by these 4 companies which are a part of it, and they are all PV manufacturers. So just to understand what the project is, it's basically circular manufacturing to complete the entire loop and looking at how the cutting edge technologies can help with this particular process in terms of taking the raw materials, the production, the supply chain, the manufacturing, as well as the disposal. So the entire idea is to have the recycling aspect, reusing in terms of the disposable, so that we can get back the materials in the most sustainable fashion. Then just to have what exactly is the difference and what the research is about, which I mentioned before, the current procedure being from the design to following the material procurement, manufacturing, logistics, use, and in the end, it's disposed of. But what the Circman is trying to do is to look at the circularity in every aspect of these stages, and in the end, to finish the entire loop, and so that the remnants can actually go back into the design process. As I've already mentioned before, but in order to do this, there are certain technologies which are being looked into, some of them being machine learning, cognitive digital twins, blockchain, AI, etc. And the whole idea is to have all of these, but with the human in the loop. Now, just to go slightly more in detail of the goals, the idea is to have the less amount of reduction. It cannot always be zero, but to reduce as to what is already existing, to be able to track the materials and their validation, to know, like, currently the products are being transported mostly from outside the European Union, and it may continue to do so. But the idea is to bring that down and to lower the overall energy consumption from right from the manufacturing to transportation to implementation, as well as the disposal. Then with all of these in mind, but to also increase the efficiency of these photovoltaics and boosting the product circularity, which I've already mentioned before. This is just compressing it into one, and minimizing the environmental impact, just like how the entire idea to reduce the carbon footprint and make it more sustainable, cutting down on the material waste, and optimizing the circular manufacturing. So it's basically the same thing. Now, how to do this is basically like the use of the data integration, dynamic lifecycle insights, smart production planning. This is all to, let's say, like, to use all of these technologies, which are here, like transparent, traceable supply chains, scalable and future-ready solutions. Like I mentioned before, all of this is going to be using this part of the technology, which is AI-driven machine learning, cognitive digital twin, circular and life cycle assessment, human in loop, and digital product material passport. So taking these technologies wherein you have the input to a particular technological aspect and what it should be able to derive. How do I explain this? The human intervention in general has to reduce to an extent that these technology is able to take over, but at the same time, we need the human intervention to reduce the amount of, let's say, the defects or the cracks or the problems which are arising at the current moment. And to be able to do all of this with the blockchain, so that to be able to access each of these technologies which are being developed across the different stages, the entire procedure and the time that it takes is, the effort is reduced on the human nature. Then what we did as Polemy was we did the literature review for this project. And the best idea was to do the analysis of the practices which were existing and do the methodological framework. Now, for all the researchers here, we followed the same, let's say, like the constant methodological mixed approach to be able to do this analysis. And we went one by one at the factory level, manufacturing level, supply chain level, product level. But to compress it, it was mostly on the lines of using the international standards to be able to justify like what is already existing in terms of the eco-design, end of life. And at the same time, we used two examples, which was reskin and Sautille. And Sautille has to be one of the tiles which have been developed in Polemy itself. And the technologies which have already been mentioned before, I'm trying to, okay. Now, the gap analysis was in terms of what has been identified as to what is really existing is the fact that the infrastructure to be able to make it like a closed loop at the moment is limited. And the end of life cycle collection rate is less than 40%. Then there are fragmented regulations and lack of harmonized eco-design standards within the European Union as well as international forum. And there is, with every company which is working on its own, the idea to be able to exchange of data and knowledge at the moment is slightly on the backhand compared to how it can be in the future. And the compatibility in terms of the technology which is going and what is really like how much of it can actually be implemented in the current technologies for the materials which can be recycled. And in terms of the roadmap and recommendations, it was mostly the entire goal of this project was defined on how economic incentives are some of the biggest incentives after the sustainability, because you need to be able to save that money in order to be able to produce what is existing and what can actually be good for the production and everything. And the adoption for the various technologies, the investment for R&D, the policy alignment with the EU Circular Economy Action Plan and Eco Design for Sustainable Products, and promotion of the cross-sector collaboration and standardization spanning beyond PV. And to conclude, to look at the whole thing, even with the technologies, is basically digitalization of the entire procedure, and to get the real-time evidence-based, okay, never mind. Impact is to enhance the sustainability, reduce waste, and strengthen European supply chain. And the future aspect of Circman is to expand the research into a much broader industrial use and to develop different kind of technologies for this PV which are already existing. Thank you.
Thank you so much. I think that was the last two presentations. We're concluding also the outlook and the carbon footprint of PV modules, which certainly also triggers some questions. So before we on the podium put the question, I asked the auditorium, are there particular questions to the presenters? So far not. So now, then I would have one, because I think the last speaker, she mentioned the eco-design standards, but what is actually a criticism? Because they do not yet exist, or because they are in preparation? They will come, I think, by the end of the year, something like this, that we will have eco-design labels on PV modules. And can you include this in your modeling?
Sorry, regarding this, I am actually not the correct person to answer this question. I'm sorry, but then I can always ask the coordinators and the people who are actually doing the research on this and get back to you.
Mm-hmm.
So.
Okay. So in principle, the same goes to the previous speaker, Alexa. I was wondering, you had these tables at the end, which were talking about the CO2 footprint of PV modules. I didn't see, but maybe I missed it, the comparison with glass facades.
Well, it is a big problem. So actually the technique is there. You can recycle glass facades, aluminum facade, anything. But the problem is how to get the material. Mm-hmm. And there's really a missing lag between deconstruction industry and also the producers. And you did not get the material at the moment. For example, the glass recycling is less than 5%. Aluminium from facades is around about 65% at the moment. Plastic or PET, it's about 40%, but special glass is just 5%. There's no sampling system. That all the glass from windows and facade runs into bottles. Mm-hmm. So it's a downcycling process, it's not a recycling.
Okay. No questions so far, yeah? Okay. Your questions?
Yes.
Yeah, have your question?
Yeah.
Have your question?
Well, on behalf of all the speakers and the chairman and myself, and thank you for listening to all this wonderful speech. And let us hope that PV will make a mark for our future and for climate change. Thank you very much. We end the meeting.
Thank you very much. We have not yet finished because we are getting into the closing session. And for that, I would ask our chairman, Francesco Frontini, and Giorgio Ponderini on the floor here to give us some farewell or maybe some key takeaways from this conference.
So we will not keep you long because we guess you're tired, but we hope you had a wonderful experience in these 2 days in Florence. So it's just to say thank you to you for participating, for especially those of you still in the room until this late hour. As we mentioned previously on the conference website, you already find some of the pictures that were taken in these days and the link to the Flickr page where you can download the pictures where most of you are portrayed. So I also want to thank again our sponsor who made this conference possible, Ecoprogetti, Next to Sun, 3S, Standex, and of course, Key, the Energy Transition Expo. As I mentioned, the website contains the picture on the LinkedIn page of the project. We try to cover also this second day of the conference. And from our side, the data, we would like to give a hint about this other initiative that we are organizing here in Florence together with the University of Florence, the MedGreen Forum that will take place here in Florence in April. So if you're interested, try to get more information on the website. And for last concluding words, I give the floor to Francesco, who was the amazing chair of this conference, and see you in 2026.
So, first of all, congratulations, you made it. So we made it. So we are the brave one that stayed till the very end of this too intensive journey. So I'm really happy that we still have people in the room listening to the last session that was also very, very interested. So I want to say that your commitment reflects really the same resilience that we need if we want really to push forward IPV in our society, in our world. So it's now very, very difficult for me to give you the full highlight of this conference. I mean, the program, you have 30 minutes. So if you have time, we can take the last 30 minutes to wrap up all together the highlight of this session. But I think it's better if I keep short. So all the speakers gave us really insight in the different possibility offered by IPV, integrated PV, in our society. So if you remember, we have organized this conference into 4 main pillars, tackling building integrated photovoltaics. It's the one that has a longer history in comparison to other, and where I think also the other possible integration can learn from. Then we also had sessions on agri-PV, especially yesterday, but also on Monday with the first Italian conference on agri-PV, where we learned that also biodiversity, nature, and lands needs attention and need to be considered when you are planning an agrivoltaic system. We had also yesterday at the very end a very nice and deep discussion on vehicle integrated PV. I think this topic is one of the the youngest one, where we only have few players active, especially in Europe, on this topic, but where I learned that the potential is enormous. If I remember correctly, only considering tracks and trails, we have about 4 million tracks running every day among cities, among places. So the potential is really huge, especially if we consider that we have energy moving around where it is needed. So we can produce energy on vehicles, but then we can move energy where it is needed, where we have the consumption, where the people that need power in order to power their system. And what we learn also on vehicle is that where for tracks and trail, we can look and develop new solution, lightweight solution, very, very efficient, but also quite cost effective. On passengers vehicles, we may need to work hard in order to make these lightweight PV modules also nice and beauty colored in order to be able to answer the needs of the customer, of everyone. Then we tackle again the topic of BIPV. I mean, I think the most of the presentation were dealing with BIPV. I mentioned it's a more mature market, and their reliability was one of the major concerns and one of the major topics. On the one hand, we have several applications, several products already available, already mature. I take the opportunity also to thank our partner, our industrial partner, that show up with several products that are available and with a lot of installation. But on the other hand, we need to carefully design both the modules, both the technology, but also the system. And we learned also from the first session where we had this relevant speaker from Polimi, from Renzo Piano Building Workshop, and for Arup, how is important the process and how we manage the process, and how it is important to have the right client defining the right targets, the right objective. Without having a clear objectives, it's very difficult to meet the target. And this was also, I think, the voice of the industry that we heard today when we had this panel discussion moderated by David, where I clearly understood that if we really want to keep the innovation of IPV in Europe, we really need to fix our targets, what we really want to achieve, and how we should support our local stakeholders and our local manufacturer. And when we consider BIPV, IPV, vehicle integrated PV infrastructure, as we also learned in the last session, probably we need to really consider that we need competence, but we need competence on-site. We need local players, local stakeholders that are proud, that are interested to develop new solution and new opportunity. So one of the lessons learned is that if we really want to achieve, and if we want really to meet the target of the energy transition, a full decarbonized society, we really need to start to speak loud, start to discuss, not alone within scientists, as we are normally used to do it. I'm a researcher, I'm a professor, and normally used to discuss with my colleagues, but really to open this discussion involving other players, researcher, manufacturer, architects, engineer, physicists, policymaker. This is also very, very important. We also had some speech from policymaker, municipalities, and and also I also would like to have also students here. Maybe next year we can also invite students from the university that belonging to us, that are connected with us, because I think we also have to train the new generation that will be the architects, the engineers of the future. So saying that, I would like again to thank Giulio. I mean, you made really a good job. I think now we can really relax. I would like to for sure, Angela and the whole ETA Florence team, the organizer, for the logistics, for the presentation, and last but not least, all speakers, moderators, that they provide on time their highlights. I think we will take some time in the next days to prepare a sort of resume and highlight of this presentation that will be shared with everyone. It will take some time because, I mean, we had really dense session. And then I also want to remember, especially the speaker, that there is an opportunity to submit a full paper. So take a look on the website. There is a dedicated session for that. And a survey will be shared soon. Also, it's really important to receive your feedback, positive or negative. I mean, we really want to improve. As Giulio mentioned, we will have a third edition. Hopefully, we will have a fourth and a fifth. And we always want to improve it. So please take few times to answer this survey. So saying that, thank you for being with us, and thanks for your contribution.